Hello, everyone. Welcome back. So excited. Today we are here to see, like, today I'm thinking of the streaming session as somewhat different. I'm going to do a course during the live stream, which is offered by DeepLearning.io, but they have their proprietary resources, which I cannot live stream uh, in my YouTube channel. So I have shared the link in the, if you see in the description, I have shared the link. So you can click on that link and you can follow along. And then in between, after every session, we can have a discussion or conversation about the course and the topic that we go through in that particular course. And it is available for free to watch for anybody. So let's get started. I'll post the link for the um, link for the course in the comment as well, and it's already available in the description. Feel free to ask me any question that you have.
Welcome to how Transformer LLMs work. In this course, you learn about the main components of the LLM transformer architecture that has transformed the field of language processing. I'm delighted that instructors for this course are Alammar and Maarten. In their book, Hands-on Large Language Models, Jay and Maarten beautifully illustrated the underlying architecture of LLMs and provided insightful explanations of transformers.
Thanks, Andrew. I'm so happy to be here today and to have the opportunity for Maarten and me to teach this course. We wrote our book to provide an easy to understand introduction to transformer-based LLMs. This course allows us to present that information in person. Our hope is that as you leave this course, you will be able to read through papers describing models and understand the details that are used to describe these architectures. And these intuitions will help you use LLMs well too.
Let me add that it is a pleasure to work with you on this, Andrew. I've taken so many of your courses over the years and appreciate all your effort into making machine learning and AI accessible to all. We're so happy to add this course to the effort.
Thank you, Maarten and Jay. It's so good to work with both of you. Let me introduce the main topic of this course, the transformer. The transformer architecture was first introduced in the 2017 paper Attention is All You Need by Ashish Vaswani and others for a machine translation task. The idea was to say input an English sentence and have the network output a German sentence. This same architecture tended to be great at inputting, say, a prompt and outputting a response to that prompt, like a question and the answer to that question. And so this whole parallel the early rise of large language models. The original transformer architecture consisted of two main parts. There's an encoder and a decoder. Consider translating English into German. The encoder pre-processes the entire input English text to extract the context needed to perform the translation. Then the decoder uses the encoded context to generate the German. The encoder and the decoder form the basis for the models used in many language models today. The encoder model provides rich context-sensitive representations of the input text and is the basis for the BERT model and most of the embedding models used in RAG applications. The decoder model performs text generation tasks such as summarizing text, writing code, answering questions, and is the basis for the most popular LLMs such as those from OpenAI, Anthropic, Cohere, and Meta. Let's go over what you learned in this course. You first delve into recent developments in LLMs to see how.
Okay, let's look into that basics of transformer architecture once again. So exploring the encoder and decoder model. So they mentioned like it is based on a paper called as Attention is All You Need. That is the original transformer architecture. And it is based on a encoder and decoder. It consists of an encoder and decoder. Encoder encodes the input into and then populate all the context or outputs all the context that is given in the input, and then decoder is the one which reads from the input and converts it as an output. So let's clearly see it once again.
The encoder model provides rich context-sensitive representations of the input text and is the basis for the BERT model and most of the embedding models used in RAG applications. The decoder model performs text generation. The transformer architecture was first introduced in the 2017 paper Attention is All You Need by Ashish Vaswani and others purpose for a machine translation task. The idea was to say input an English sentence and have the network output a German sentence. This same architecture turned out to be great at inputting, say, a prompt and outputting a response to that prompt, like a question and the answer to that question. And so this helped herald the early rise of large language models. The original transformer architecture consisted of two main parts. There was an encoder and a decoder. Consider translating English into German. The encoder pre-processes the entire input English text to extract the context needed to perform the translation. Then the decoder.
Okay, so as I said and reiterating the same thing, encoders takes in the input and extracts all the context information. It extracts all the context information from the input.
Encoder uses the encoded context to generate the German. The encoder and the decoder form the basis for the models used in many language models today. The encoder model provides rich context-sensitive representations of the input text and is the basis for the BERT model and most of the embedding models used in RAG applications. The decoder model performs text generation tasks such as summarizing text, writing code, answering questions, and is the basis for most popular LLMs such as those from OpenAI, Anthropic, Cohere, and Meta. Let's go over what you learned in this course. You first delve into recent developments in LLMs to see how a sequence of increasingly sophisticated building blocks led to the development of Transformer. You then learn about tokenization, which consists of taking text and breaking it down into tokens that comprise words or word fragments that can then be fed into the LLM. After that, you gain intuition about how the transformer network works, focusing on the decoder-only models. A generative model takes in a text prompt and it generates a text in response by generating one token at a time. Here's how the generation process works. The model starts by mapping each input token into an embedding vector that captures the meaning of that token. After that, the model passes these token embeddings through a stack of transformer blocks, where each block is a specific neural network architecture that was designed to learn flexibly from data and also scale well on GPUs. So you learn how each block is made up of an attention layer and a feed-forward network. The model then uses the output vectors of the transformer blocks and passes them to the last component, the language modeling head, which generates the output token. I'd like to thank, from DeepLearning.AI, Jeff Lardwig and Hara Salami for helping with this course. By the way, I know that transformers might seem a little bit like magic to some people, and in fact, one common experience after you learn how transformers work is I've heard some people go, oh, that's it? And I think part of the reason for that reaction is the magic of LLMs actually comes from two parts. One, the transformer architecture, which you learn is well worth learning. And second, all the incredibly rich data that the models learn from. So while the magic of LLMs comes not just from the transformer architecture, but also from the data, having a solid intuition of what this architecture is doing will give you better intuitions about why they behave in certain ways, as well as how to use them. Let's get started with Maarten in the first lesson.
Okay, that wasn't very basic, but it is interesting concept. So let's look into the same thing again, like what you will learn section. So here, here we were given a preview of what we are going to learn in this course. Let's take a look into that once again and try to grasp it.
Welcome to How Transformer LLMs Work. In this course, you learn about the main components of the LLM transformer architecture that has transformed the field of language processing. I'm delighted that instructors for this course are Jay Alammar and Maarten Grootendorst.
Okay, not here. I'm interested in the preview.
Recent developments in LLMs to see how a sequence of increasingly sophisticated building blocks led to the model transformer. transformer. You then learn about tokenization, which consists of taking text and breaking it down into tokens that comprise words or word fragments that can then be fed into the LLM. After that, you gain intuition about how the transformer network works, focusing on the decoder-only models. A generative model takes in a text prompt and it generates the text in response by generating one token at a time. Here's how the generation process works. The model starts by mapping each input token into an embedding vector that captures the meaning of that token. After that, the model passes these token embeddings through a stack of transformer blocks, where each block is a specific neural network architecture that was designed to learn flexibly from data and also scale well on GPUs. So you learn how each block is made up of an attention layer and a feedforward network. The model then uses the output vectors of the transformer blocks and passes them to the last component, the language modeling head, which generates the output token. I'd like to thank, from DeepLearning.AI, Jeff Lardwig and Hara Salami for helping with this course. By the way, I know that transformers might seem a little bit like magic to some people, and in fact, one common experience after you learn how transformers work is I've heard some people go, oh, that's it. And I think part of the reason for that reaction is the magic of LLMs actually comes from two parts. One, the transformer architecture, which you learn is well worth learning. And second, all the incredibly rich data that the models learn from. So while the magic of LLMs comes not just from the transformer architecture, but also from the data, having a solid intuition of what this architecture is doing will give you better intuitions about why they behave in certain ways, as well as how to use them. Let's get started with Maarten in the first lesson.
Okay, in that first section, all we saw was basically, let me pull up my notes. So we saw that, we discussed about the code structure and we discussed about the author. And then based on the 2017 paper, Attention is All You Need by Ashish Vaswani and others. So that is the transformer architecture that we are discussing today. Originally, it was designed for machine translation between English to German. And then the same architecture has been now used to prompt the response generation in modern LLMs. So in LLMs mainly consists of transformer architecture mainly consists of encoder and decoder structure. So encoder always takes the input text and extracts all the context information needed for the task and provides the rich context sensitive representation of the input data and then forms the basis for all the models. And also and most embeddings used in the RAG applications as well. RAG we saw last week, retrieval augmented generation model. So basically it is used for, like, for example, just to give a simple example, if we have a corporate office and if we don't want to expose all our documents to some public LLMs like ChatGPT or OpenAI models, basically we can connect it to RAG and provide all of our data there, and then the already trained models can connect to the tools or our data, our proprietary data, and search the data and also include it in their response. So the roughly speaking, that's the RAG architecture. So let's see. Decoder. Decoder usually reads the encoder's context and generates the output and performs the text generation tasks, mainly summarizing, code writing, and answering all the questions. So it retrieves the context and then it generates everything. Forms the basis of popular LLMs from OpenAI, Anthropic, Cohera, and Meta. Okay, recent developments in LLM and evolution of transformer architecture, that's what we are going to discuss moving forward. And tokenization, how the words are broken down into tokens and word fragments. Transformer network mechanism focused on decoder only models, mapping input tokens to embedding vectors. We need to still understand what are embedding vectors. Processing through transformer blocks, attention layers. So we will learn about these attention layers and feed forward networks. And language modeling, head generating output tokens. So all of these things, the magic of LLMs comes from the architecture and the rich training data. So all these are the things that we are going to learn going forward in the session. So let's move forward to the next chapter.
You will learn the evolution of how language has been represented numerically. We'll start with bag of words, an algorithm that represents words as large sparse vectors or arrays of numbers, which simply record the presence of a word. Then word-to-vec, whose word representations capture the meaning of words in the context of a few neighboring words. Finally, transformers, whose dense vectors capture the meaning of words in the context of a sentence or a paragraph. Alright, let's jump in. I have some illustrations that will help clarify these ideas. Although we will explore a more recent history of language AI and language models, it is important to understand where we started. Earlier techniques, such as bag of words and word-to-vec, have been arguably the foundation of what we're using today. Although they lack contextualized representations, they are often a good baseline to start with. We call these non-transformer models, since today's models are typically powered solely by transformer models, in contrast to these strong baselines. Then we have encoder-only models, which are great at representing language in numerical representations. In contrast, decoder-only models are generative in their nature. Their main usage is to generate text. And finally, we have encoder-decoder models that attempt to get the best of both worlds. You will learn about these non-transformer models, encoders, decoders, and how they relate as we explore this more recent history of language AI. Language, however, is a tricky concept for computers. Text is unstructured in nature and loses its meaning when represented by zeros and ones, or individual characters. As a result, throughout the history of language AI, there has been a large focus on representing language in a structured manner so that it can more easily be used by computers. From generating text to creating numerical representations and classifying textual input. These are just a few of the numerous tasks you can do with language AI. At the start of this language AI field, the focus was mainly on representing language to analyze unstructured data. A first and still very relevant method is by representing language as a bag of words. Imagine you have some input text. That is a cute dog. To represent this sentence, you can break it up into smaller pieces. To do so, you split the text into words by separating them through a white space. This process of converting the input text into pieces is called tokenization, and each individual word is called a token. Note that a token can be even smaller than an entire word, but we will go through tokenization in the next lesson in more detail. You can perform the same tokenization process with another document. My cat is cute. Although similar documents, they do contain different words and have a different meaning. Now that you are left with two sets of tokens, you can create something called a vocabulary. This vocabulary contains all unique words or tokens found in both input documents. As such, the vocabulary will contain fewer words than the amount of tokens that were generated. And we typically refer to the number of tokens or words in the vocabulary as the vocabulary size. To then represent one of our inputs with numerical values, let's focus a bit on our second input. My cat is cute. This input has 4 tokens that match with some of the words in the vocabulary, but not all. You can then count how often a certain token appears in the vocabulary that we already created. In this case, each token appears once. However, you will also have to take note of the words in the vocabulary that do not appear in the input. A sentence not only gives meaning to the words it contains, but also to the words it doesn't. Now that you have counted how often the words or tokens of our input appear in the vocabulary, you have created your numerical representation. This is called a bag of words and does nothing more than counting individual words that appear in the vocabulary. Therefore, the numerical representation of my cat is cute is 01010111 in that specific order. The order is important as it allows us to compare different sentences to one another. In practice, we call this a vector representation, a list of numerical values that represents the input. In this example, these values are counts and have an explicit meaning, namely the number of times a word in the vocabulary appears in the input. Vector representations in more complex and advanced models typically do not have such an intuitive meaning and have values between 0 and 1. Let's go to the next video and learn how these vector embeddings are created.
I see a couple of comments. So hi Vijaya. So today we are learning about transformers, diving a little deep about like how LLMs work, and the main architecture is in LLM is transformer architecture. We are trying to break it down and go in deep about like how LLMs work and what are embeddings and what are the architectural concepts involved in transformers and all those things. So let's dive in and try to understand each and everything there. So in the first chapter, Andrew spoke about the transformer architecture and the evolution of it, how it started, um, and what are the main components in the transformer architecture. He spoke a little bit about encoders and decoders, and also provide a glimpse of like what we consist in the overall course. And in the second one, like the author spoke about the author of the book. I think Jay spoke about language as a baggage, as a bag of words, as a concept. So we can look into that again, or we can move into the next topic now. Let's glance it again and try to narrow it down, or try to pin down our understanding into that one, and then we can move on to the next topic. Does anybody have any questions? Let me know.
In the next several videos, you will learn the evolution of how language has been represented numerically. We'll start with bag of words, an algorithm that represents words as large sparse vectors or arrays of numbers, which simply record the presence of a word. Then word2vec, whose word representations capture the meaning of words in the context of a few neighboring words. Finally, transformers, whose dense vectors capture the meaning of words in the context of a sentence or a paragraph. Alright, let's jump in. I have some illustrations that will help clarify these ideas. Although we will explore a more recent history of language AI and language models, it is important to understand where we started. Earlier techniques, such as bag of words and word2vec, have been arguably the foundation of what we're using today. Although they lack contextualized representations, they are often a good baseline to start with. We call these non-transformer models, since today's models are typically powered solely by transformer models, in contrast to these strong baselines. Then we have encoder-only models, which are great at representing language in numerical representations. In contrast, decoder-only models are generative in their nature. Their main usage is to generate text. And finally, we have encoder-decoder models that attempt to get the best of both worlds. You will learn about these non-transformer models, encoders, decoders, and how they relate as we explore this more recent history of language AI. Language, however, is on transformer models and
So in this screen or in this PPT, basically he explained the evolution of all the architectures or the algorithms that are being used to transform language. So the early evolution included, or early technique included using of bag of words, and then we started using word to vec, and then 2017 is the attention is all you need. So we started with that, and then here the classification has been made as all the gray ones are non-transformer models, and all the blue ones are encoder only models. So this BERT, Distil, BERT, and Roberta, all these encoder only models. There are decoder only models as in GPT, GPT-2, GPT-3, and Chat GPT. And then there are encoder and decoder models, T5, Switch, and Flan T5, all these things. Let's see. Let's move ahead.
encoders, decoders, and how they relate as we explore this more recent history of language AI. Language, however, is a tricky concept for computers. Text is unstructured in nature and loses its meaning when represented by zeros and ones or individual characters. As a result, throughout the history of language AI, there has been a large focus on representing language in a structured manner so that it can more easily be used by computers.
So, Ojas Srivastav, thank you very much for the feedback. Yeah, I'm learning about how Transformer works and how LLMs work in like diving deep a little bit. Last week we looked into the basic or the introduction of LLMs or large language models. So let's see. And I'm not sure about the voice. If it is, you are mentioning the voice is low, so let me test it. I'll just open it in my phone and see. The voice, if it is, you are mentioning the voice is
History of language AI and language models, it is important to understand where we started. Earlier technique
In architecture, developers create inputting, say, a prompt and
a couple of comments. So hi Vijaya. So today. Hey, Ojas. So I hope the voice is audible now. Like I, I checked it and it looks like healthy as of now. So let me know if there are any issues. But uh, but thanks for the feedback.
text to creating numerical representations and classifying textual input. These are just a few of the numerous tasks you can do with language AI. At the start of this language AI field, the focus was mainly on representing language to analyze unstructured data. A first and still very relevant method is by representing language as a bag of words. Imagine you have some input text. That is a cute dog. To represent this sentence, you can break it up into smaller pieces. To do so, you split the text into words by separating them through a white space. This process of converting the input text into pieces is called tokenization, and each individual word is called a token. Note that a token can be even smaller than an entire word, but we will go through tokenization in the next lesson in more detail. Transformer models, encoders, decoders, and how they relate as we explore this more recent history of language AI. Language, however, is a tricky concept for computers. Text is unstructured in nature and loses its meaning when represented by zeros and ones or individual characters. As a result, throughout the history of language AI, there has been a large focus on representing language in a structured manner so that it can more easily be used by computers. From generating text to creating numerical representations and classifying textual input. These are just a few of the numerous tasks you can do with language AI. At the start of this language AI field,
I did not understand the third one. Basically, one is generating the output or the numerical output from the text input. Second one is embeddings, converting it into numerical values or embeddings. And third one, classification. What does that mean?
at the start of this language AI field, the focus was mainly on representing language to analyze unstructured data.
Yeah.
A first and still very relevant method is by representing language as a bag of words. Imagine you have some input text. That is a cute dog. To represent this sentence, you can break it up into smaller pieces. To do so, you split the text into words by separating them through a white space. This process of converting the input text into pieces is called tokenization, and each individual word is called a token. Note that a token can be even smaller than an entire word, but we will go through tokenization in the next lesson in more detail. You can perform the same tokenization process with another document. My cat is cute. Although similar documents, they do contain different words and have a different meaning. Now that you are left with two sets of tokens, you can create something called a vocabulary. This vocabulary contains all unique words or tokens found in both input documents. As such, the vocabulary will contain fewer words than the amount of tokens that were generated. And we typically refer to the number of tokens or words in a vocabulary as the vocabulary size. To then represent one of our inputs with numerical values, let's focus a bit on our second input. My cat is cute. This input has 4 tokens that match with some of the words in the vocabulary, but not all. You can then count how often a certain token appears in the vocabulary that we already created. In this case, each token appears once. However, you will also have to take note of the words in the vocabulary that do not appear in the input. A sentence not only gives meaning to the words it contains, but also to the words it doesn't. Now that you have counted how often the words or tokens of our input appear in the vocabulary, you have created your numerical representation. This is called a bag of words and does nothing more than counting individual words that appear in the vocabulary. Therefore, the numerical representation of my cat is cute is 01010111 in that specific order. The order is important as it allows us to compare different sentences to one another. In practice, we call this a vector representation, a list of numerical values that represents the input. In this example, these values are counts and have an explicit meaning, namely the number of times a word in the vocabulary appears in the input. Vector representations in more complex and advanced models typically do not have such an intuitive meaning and have values between 0 and 1. Let's go to the next video and learn how these vector embeddings are created.
Okay, let me summarize this for now. So, in this chapter, mainly the course author spoke about the bag of technique called as bag of words, which was used. So, it is a simple concept like, okay, yeah, even before that, he mentioned about the evolution of the language representation. Bag of words as a, one of the early algorithm using large sparse vectors that simply record word presence. That's what he explained in the later ones. Why I'm mentioning it as sparse? Because like he created something called as a vocabulary. Like in vocabulary, each word has a representation, and basically for an input, like if the word is not contained, then also it is mentioned as 0, and then it was considered. So it is a Okay, let me open my notes. So it is a sparse representation of the word. And then there was another representation called word to vector or word to vectors, captures the word meaning in the context of the neighboring words as well. And transformers, like he will talk about this one in detail in the next sections, I think, transformers as well. But this is the evolution of how the language models or the language representation went. Sorry, yeah. So, and then there are model types and classification. So in that model types, he mentioned there are non-transformer models, encoder-only models, for example, BERT, Distilbert and Roberta, and decoder-only models, GPT, GPT-3, ChatGPT, and all that, which are basically generators. And encoder and decoder models combines the benefit of both the approaches. So these are a few of the examples. And language AI applications, there are three primary use cases that were introduced. One is generating the text output or the creation, and then creating numerical representation or the embeddings, and third is classifying the textual inputs. Focus of early language AI was mainly on representing the language to analyze the unstructured data. So language was not a structured data as compared to, like, if you consider programming language or something which a machine can understand, those were structured data, but language were unstructured data. So the early focus of the AI was mainly to represent and analyze this unstructured data. And tokenization fundamentals, converting the input text into smaller pieces called tokens. Tokens are typically created by splitting text into white spaces. But it is not as it is. Don't take it for the face value. There are some more nuances to it. A token can be a full word or even smaller fragments of the word as well. Example, that is a cute dog, breaks into individual word tokens. That is a cute dog, can be individual tokens. Bag of words techniques was explained in brief. So vocabulary creation. First thing is, like, whenever an input is provided, the vocabulary is updated by adding the token into the vocabulary. All unique words or token from the input documents are collected, and that makes the vocabulary creation. And vocabulary size refers to the number of unique tokens. And counting process, for each input count how often each vocabulary word appears. And words not appearing in the input are also tracked. That's why it becomes a sparse data or sparse collection of the data. Assigned count as 0. Vector representation, numerical list representing token inputs in the vocabulary order. My cat is cute becomes 0 1 0 1 0 1 1, like as it was represented in that. If you visualize, let me go back to that one. If you visualize the same thing, so my cat is cute, so that is represented as 0 1 0 1 0 1 0 1 1, because this is the entire vocabulary. That is the cute dog, my cat, that is the entire vocabulary. So we are representing based on the position of those individual words or tokens in that vocabulary. Let's go back to the notes. And then yeah, and then counting process that happened. More advanced models use vector representations with values between 0 and 1, with values between 0 and 1, as it was explained. So in the next section we will see in detail about the vector representations and the embeddings. So clarification on, okay, yeah, so let's move on to the next chapter and dive into that. Let me know if you have any questions into that one. Okay, so in between, Ojas has a question. Yeah, Ojas, I'm an engineer, but why am I studying? Just to keep myself updated, and also as an engineer, I think it's lifelong. We need to keep learning. I guess that's what I believe in, um, and it makes me happy, irrespective of what benefits we are gonna get or anything. Staying updated with the latest developments and latest technologies. So that is something which makes me happy. And also um, teaching it to others, that's an added advantage if someone gets benefit out of it. Let me know if you have any other questions. We can talk about it. Like, let's finish this course, and with every break I'll try to answer any questions that you have.
Let's explore how these more complex vector embeddings are created. Note that bag of words, although an elegant approach, has a flaw. It considers language to be nothing more than an almost literal bag of words and ignores the semantic nature or meaning of text. Released in 2013, Word2Vec was one of the first successful attempts at capturing the meaning of text in embeddings. To do so, Word2Vec learns semantic representations of words by training on vast amounts of textual data, like the entirety of Wikipedia. To generate these semantic representations, Word2Vec leverages neural networks. These networks consist of interconnected layers of nodes that process information. Neural networks can have many layers, which each connection has a certain weight depending on the inputs. These weights are often referred to as parameters of the model. Using these neural networks, Word2Vec generates word embeddings by looking at which other words they tend to appear next to in a given sentence. You start by assigning every word in your vocabulary with a vector embedding. Say 5 values for each word is initialized with random values. Then in every training step, you take pairs of words from the training data and the model attempts to predict whether or not they are likely to be neighbors in a sentence. During this training process, Word2Vec learns the relationship between words and distills that information into the embedding. If the two words tend to have the same neighbor, their embeddings will be closer to one another and vice versa. The resulting embeddings.
Okay, let us repeat the same thing. This is an important concept. So here we are trying to look at the correlation between the words. Like now, for example, here he is explaining cat and cute. These are the two words. What is the likelihood of having cute as or the other word as the neighbor of each other? Basically, this is one of the other representation which was kind of this algorithm was written in 2013, and this is what is explained as word2vec or the vector embedding. So let's look into this once again from the beginning.
Or how these more complex vector embeddings are created. Note that bag of words, although an elegant approach, has a flaw. It considers language to be nothing more than an almost literal bag of words and ignores the semantic nature or meaning of text. Released in 2013, Word2Vec was one of the first successful attempts at capturing the meaning of text in embeddings. To do so, Word2Vec learns semantic representations of words by training on vast amounts of textual data, like the entirety of Wikipedia. To generate these semantic representations, Word2Vec leverages neural networks. These networks consist of interconnected layers of nodes that process information. Neural networks can have many layers, which each connection has a certain weight depending on the inputs. These weights are often referred to as parameters of the model. Using these neural networks, Word2Vec generates word embeddings by looking at which other words they tend to appear next to in a given sentence. You start by assigning every word in your vocabulary with a vector embedding. Say 5 values for each word is initialized with random values. Then in every training step, you take pairs of words from the training data and the model attempts to predict whether or not they are likely to be neighbors in a sentence. During this training process, Word2Vec learns the relationship between words and distills that information into the embedding. If the two words tend to have the same neighbor, their embeddings will be closer to one another and vice versa. The resulting embeddings capture the meaning of words. But what exactly does that mean? To illustrate this phenomenon, let's explore an example. Assume that you have an embedding for the word cats. This embedding has generated values between -1 and 1. Embeddings attempt to capture meaning by representing the properties of words. For instance, the word cats might score low on the properties newborn and human and fruit, whilst scoring high on the properties animal and plural. The number of properties or values an embedding has is called the number of dimensions and is generally a fixed size. The same can be said for other words, such as puppy, which scores high on animal and newborn, but low on all others. By doing this for a number of words, you can use these values to get a proxy of the meaning of these words. Note that the number of dimensions can be quite large, where it is not uncommon to see embeddings with more than 1,000 values. However, in practice, you do not actually know what these properties exactly represent, as they are learned through complex mathematical calculations. These properties do allow you to compare embeddings and therefore words with one another. Words with similar meaning will be grouped together, whereas different words are further apart. How similar or dissimilar certain words are depends on the training data. Thus far, we explored word embeddings, but there are many types of embeddings that we can use. When we talk about a model like Word2Vec that converts textual input to embeddings, we refer to it as a representation model, as it attempts to represent text as values. Imagine that you have some input. For example, the sentence, "Her vocalization was melodic." Through tokenization, you can split that sentence up into tokens. Note that this procedure is actually not splitting the input by white spaces. The word vocalization is split up into vocal and azation. The reason for this is that models that perform tokenization, also called tokenizers, have a fixed vocabulary. As such, they cannot represent all words that exist, but sometimes have to find combinations of words. You give the representation model these individual tokens, which in turn generates these embeddings, one for each token. Note that the word vocalization contains the tokens vocal and azation. So when you average the embeddings of these tokens, you get a word embedding, as it now represents the entire word. Similar techniques can be used for entire sentences to create sentence embeddings, and the same for longer texts, such as documents to create a document embedding. These are just a few of the many embeddings that exist. Join me in the next video to learn how you can encode and decode contextualized information rather than static representations.
Okay, let me gather my notes in a bit so that we can summarize it. In the meantime, if you have any questions about that particular section, let me know. So the bag of word has a fundamental flaw in it. It treats language as a literally a bag of words. Basically, it was like putting everything or trying to represent every input as a word value, even like whether the word presents in the vocabulary or not based on that, and ignores the semantic nature and meaning of the text. So it couldn't provide the meaning of the text, and also does not capture the contextual relationship between the words. It could not capture the relationship across the words. We would just know whether a single word present in the input or not. So word to vec. So he spoke about another topic called as word to vec. Word to vec is released in 2013 as one of the first successful attempts at capturing the meaning in embeddings. Embeddings is the numerical representation of the input. It learns the semantic representation by training on vast amount of contextual data. Example, the entire Wikipedia. Basically, yeah, they use something like a neural networks into that one. Basically, I'm just trying to add the same representation here. Okay. Uses neural network consisting of the interconnected layers of nodes to process information. Okay, got it. And network connections have weights and weights called parameters. So this one we saw in the previous classes or previous streams about like what are the parameters in a model and all that. Okay, how word to vec training works. Basically, it generates word embeddings by analyzing which words appear next to each other in sentences. So when we look at that large amount of data, we would assign the probability of like the of each words appearing uh, after one another in the same context. And initialization, every word in vocabulary assigned a vector embedding. Example, 5 values with random initial values. Instead of 5 values, I think it is mentioned as 1024 values there, if I was correct. So when I saw this one, so vector embeddings are represented like this. Okay, capture the meaning by representing the properties of words. Okay, here. After the training, every word in the vocabulary assigned a vector embedding, example 5 values with random initial values, takes pair of words from training data and predicts whether they are likely to be neighbors or not. Here, cats and animal, can that be a neighbor? Yes. 0.91% probability. Cats and newborn, that is a negative probability, not very likely. But cats, plural, that is a very highly likely probability. In the same way, puppy is considered as newborn, so that is a high likely probability. Puppy, plural, no, that is very least likely, so it is a negative 0.82 probability. Puppy is a fruit, no, negative 0.91 probability. So in the same way, baby, newborn, so 0.90 high probability. Apple, fruit, so that is 0.89 high probability. Apple, animal, negative probability. So in that way, the training process takes the pair of words from the training data and predicts whether they are likely to be neighbors or not, and they are represented in these vector embeddings. And learning the relationships, model distills word relationships into embeddings during the training. Words with the same neighbors have embeddings closer to one another. Okay, embeddings capture the meaning by representing the properties of words, as we saw. Generated values typically between -1 to 1, +1. Word cats might score low on properties, newborn, human, fruit, high on properties, animal and plural. Word puppy scores high on animal and newborn, but low on others. Provides proxy for the word meaning. So this is basically, with this context information, we are kind of trying to deduce the meaning of this word. So cat comes whenever, like, animal comes more uh, when there is cats, and when there is a puppy, 0.91, 0.93. So that provides the more like act like a synonym in the vector representation. Okay, next one, embedding dimensions. Number of properties or values is called the number of dimensions. So here we saw 1024 values. That means that's the dimensions. Generally, it's a fixed size. Not uncommon to see embeddings with more than 1000 values. In practice, exact meaning of properties is unknown as they are learned through complex mathematical calculations, as we saw in the other day as well. Like, uh, what is the result of a model? After we train the model, what is the result of a training? So after we train a model or train an LLM model, it generates a basically run.c file, and then another one is parameters file. Are we like, is this parameters file is anyway like deterministic? No, when we are tuning it as well, like we do not know like if we tweak which parameter, what will be impacted in the output. So but that is another research field, and there is no way to determine that as of now. And that complex calculations happens within the machine, and also there is a fine tuning process based on the human provided feedback or the curated training data, rather than taking the random Wikipedia or random internet data. If we curate the data which we are like more certain about, and we train based on that accurate data, the accuracy of the model keeps improving and the parameter keeps getting fine tuned. That's the goal. So not uncommon to see the embeddings. This is our exact meaning of the properties. Exact meaning of the properties in this case sense means I'm assuming it as parameters. Is unknown as they have learned through complex mathematical calculations. Properties alone, comparison of embeddings and words. Okay. Words with similar meaning are grouped together. Different words are farther apart. And similarity or dissimilarity depends on the training data. Okay. Representation models. Models like word to vec that convert textual input into input to embeddings are called representation models. Okay, so it is converting the textual input to numerical embeddings, and these are called representation models. Attempt to represent text as numerical values. Okay, generate embeddings for each token in the input. Okay, that's all right. Tokenization details. Tokenization does not simplify, does not simply split by white spaces. Here there is an example given. Her vocalization was melodic. So we cannot have in our vocabulary for individual, every individual, vocal as a word and vocalization as another word was melodic. The word vocalization splits into vocal and ization. It, like when ization comes, we know that okay, it will be prefixed by another word or another token for sure. It could be tokenization, vocalization, or it could be anything. So split into two tokens. What we mean to say is a single word cannot be mapped into tokens blindly. Here in this example, vocalization is split into two different tokens, vocal and ization. Tokenizers have uh, tokenizers have fixed vocabulary and cannot represent all possible words. Must find the combination of tokens to represent words not in vocabulary. Okay, I did not understand this one. Tokenizers have fixed vocabulary and cannot represent all possible words. Okay, this is fine. Must find combination of tokens to represent words not in vocabulary. Okay, so in vocabulary we might not have vocalization or tokenization, so we need to find the combination of those words to find the to uh, to get that word. Token embeddings are one embed, like we are talking about the types of embeddings. Token embeddings is one thing, one embedding generated for each token. Okay, word embeddings, when a word contains multiple tokens like vocalization with vocal and ization, averaging the token embeddings, creating a word embedding. Averaging the token embeddings, creating a word embedding. Okay, sentence embedding, similar techniques used for entire sentences. And document embedding, same approach for longer text like documents. Let's see that one in the representation that they mention. So to understand type embeddings or type of embeddings, okay, let's see here types of embeddings. So here uh, okay, input, the dominant sequence transduction models are based on complex something, and another input is my cat is cute, her vocalization was melodic, her vocalization was melodic, split into tokens. Okay, representation model, embed the input text, embedding model. Okay, token embeddings, one embedding generated for each token. Basically these are each tokens, one embedding was generated. Word embeddings, when a word contains multiple tokens, averaging the token embeddings created a word embedding. So here vocalization would be a word embedding for that one. Like we take the tokens and then we combine it. So that will, like we combine the two tokens, that will make the word embedding. So this is token embedding, individual ones. And then the sentence embedding can be the whole sentence, like my cat is cute. That entire thing can be the sentence embedding. Document embedding, the entire document, not just one sentence or one token or one word. The entire document can be represented in a specific format. When I say embedding, I meant this one, something like in this uh, format, like 1024 values or whatever the fixed value that is represented in. So that is called as document embedding. So that's about it in this chapter. Let's take a quick break, and in the meantime, if you have any questions, let me know. Otherwise, we will dive into next chapter where we will look into basically encoding and decoding context with attention. So we have a few more chapters. Let's cruise through those and finish it. Okay, let's jump back to the next chapter.
In the previous videos, we explored word and token embedding techniques, but with limited contextual capabilities. In this video, we will explore how you can encode and decode context with attention. Word2Vec creates static embeddings. The same embedding is generated for the word bank, regardless of the context. Bank can refer to both a financial bank as well as the bank of a river. Its meaning and therefore its embedding should change depending on the context. Capturing text context is important.
Okay, let me restart it. Let's start the chapter, encoding and decoding the context with attention.
In the previous videos, we explored word and token embedding techniques, but with limited contextual capabilities. In this video, we will explore how you can encode and decode context with attention. Word2Vec creates static embeddings. The same embedding is generated for the word bank, regardless of the context. Bank can refer to both a financial bank as well as the bank of a river. Its meaning and therefore its embedding should change depending on the context. Capturing text context is important to perform some language tasks, such as translation. A step in encoding this text was achieved through recurrent neural networks, or RNNs. These are variants of neural networks that can model sequences as an additional input. To do so, these RNNs are used for two tasks: encoding or representing an input sentence, and decoding or generating an output sentence. Let's explore this by showcasing how this input sentence, I love llamas, gets translated to Dutch. The text is passed to the encoder, which attempts to represent the entire sequence through embeddings. The decoder then uses those embeddings to generate language. Here it translated the English I love llamas to the Dutch ik hou van lama's. Each step in this architecture is auto-regressive. When generating the next word, this architecture needs to consume all previously generated words. For instance, you take the input I love llamas. The model then generates the first token, which is ik. To then generate the next token, the output ik is appended to the input. In step 2, the input is now I love llamas ik, which in turn generates the output how. You can continue this process at each step and continuously update the input with the previously generated token until the entire output is generated. Most models are auto-regressive and will therefore generate a single token each time. Let's explore this encoding and decoding in a bit more detail. You again start with the input sentence, I love llamas, tokenized into tokens. We can use Word2Vec to create the embeddings as the input. Although these embeddings are static by themselves, the encoder processes the entire sequence in one go and takes into account the context of the embeddings. The encoding step aims to represent the input as well as possible and generates the context in the form of an embedding. This decoder in turn is in charge of generating language and does so by leveraging the previously generated context embedding to eventually generate the outputs. As we explored previously, these output tokens are generated one at a time, which is called auto-regressive. This context embedding, however, makes it difficult to deal with longer sentences since it is merely a single embedding representing the entire input. So the single embedding might fail to capture the entire context of a long and a complex sequence. In 2014, a solution called Attention was introduced that highly improved upon the original architecture. Attention allows a model to focus on parts of the input sequence that are relevant to one another or attend to each other and amplify their signal. Attention selectively determines which words are most important in a given sentence. Take our input and output sequences for example. Words with similar meaning like I and the Dutch ik which are synonyms, have higher attention weights since they are more related. I and llamas have lower attention weights since they do not relate much to each other in this particular sentence. And the same applies to all other words. By adding these attention mechanisms to the decoder step, the RNN can generate signals for each input word in the sequence related to the potential output. You can again represent the input using word-to-vec embeddings and pass those to the encoder. Instead of passing only a context embedding to the decoder, the hidden states of all input words are passed to the decoder. A state for a word is an internal vector from a hidden layer of an RNN that contains the information about the previous words. The decoder then uses the attention mechanism to look at the entire sequence. Finally, this again generates the language. Due to this attention mechanism, the output tends to be much better since you now look at the entire sequence using embeddings for each token or word, instead of the smaller and more limited context embedding. So during generation, the model attends to the most relevant input. After having generated ik hou van, using the input I love llamas, the attention mechanism then highlights words that are more relevant in this particular example. The sequential nature of this architecture precludes parallelization during training of the model. Let's go to the next video and learn how attention is used in transformer models.
Okay, let me finalize the notes of this one and we will go over this section again. Okay, here let's talk about the limitations of word-to-vec embeddings. Word-to-vec creates a static embeddings, but where the same embeddings is generated for a word regardless of the context. For example, the word bank. Bank could be a financial bank or could be the bank that comes in context of a bank of a river. So, but still there is a single context. This limitation makes it difficult to perform context-dependent language tasks like translation, or could be anything. Even for the conversation, when somebody is talking about the financial bank, if we do not have that context, it gets difficult. Capturing context is essential. Capturing text context is essential for accurately representing word meaning. RNN were introduced as a step forward in encoding the text context. RNN is recurring neural network. These neural network variants can model sequences as an additional input. Model sequences as an additional input. RNNs perform two primary tasks: encoding or representing an input sentence, and decoding or generating an output sentence. Okay, RNNs performs two primary tasks: encoding or representing an input sentence and decoding or generating an output sentence, both. These neural network variants model sequences as an additional input, not just a single word, but the sequence also as an additional input. The architecture was demonstrated using translation from English to Dutch. I love llamas. Ik hou van llamas. Text is passed to the encoder, which represents the sorry for my attempt if I made some mistake. Encoding process. Text is passed to the encoder, which represents the entire sequence through embeddings. The decoder uses those embeddings to generate the language in the target language. Autoregressive generation. The architecture is autoregressive, meaning it generates one token at a time. When generating the next word, the model must consume all previously generated words. Basically, it's not like it generates word by word, but it needs the entire context. Basically, when it generates a sentence, like if it generates first three words, it needs all those first three words to generate the fourth word. It cannot just generate it by the previous word. So that's what. When generating the next word, the model must consume all the previously generated words. Step-by-step process. Input I love llamas generates the first token ik, and step 2 input becomes I love llamas ik and generates how. This process continues, appending each generated token to the input until the entire output is complete. Most models follows this auto-regressive approach and generate single token at each step. Encoding and decoding details. Input sentences is tokenized into individual tokens, as we saw before. Word2Vec creates embeddings as inputs, though these embeddings are static by themselves. The encoder the encoder process the encoder processes the entire sequence at once and takes context into account. The encoder processes the entire sequence at once and takes context into account. Okay. Context embedding, the encoding step generates context in the form of an embedding that represents the input. Okay. Let's see that. Okay. Embedding that represents the input. The decoder leverages this context embedding to generate the output tokens auto-regressively. Okay, let me show that one. Okay, you can see that in this representation, encoding and decoding the context. Okay, so you can see here, the input is encoded into a context embedding as well. Like there will be token embedding that is performed by word2vec embeddings. Using those, there is a context embedding that is created. Using the context embedding, decoder will generate the output. The decoder leverages this context embedding to generate the output tokens auto-regressively. Okay, problems with single context embeddings. Using a single embedding to represent the entire input creates difficulties with longer sentences. So the entire input, when it is like this, then it was easy. But when there is a longer sentences, a single context could be a problem. A sentence embedding may fail to capture the full context of long and complex sentences or complex sequences. Introduction of attention mechanism. In 2014, attention was introduced as a solution that significantly improved original architecture. Attention allows a model to focus on parts of the input sequence that are relevant to one another and amplify their signal. Okay, attention allows a model to focus on parts of the input sequence that are relevant to one another and amplify their signal. Okay, let's see what is that one. Core concept. Attention allows models to focus on parts of the input sequence that are relevant to one another and amplify their signal. Attention selectively determines which words are most important in a given sentence. For example, in this one, I love llamas or ik hou van llamas. You can see which word is high attention and which one is low. That is represented here. And how attention works. Attention weights. Words with similar meaning have higher attention weights because they are more related. Example, I and Dutch ik synonymous have higher attention weights. I and llamas have lower attention weights as they don't relate much to each other. Okay. each other in the sentence. The RNN with attention mechanisms can generate signals for each input word related to the potential output. Improved architecture and attention. Input is represented using word-to-vec embeddings and passed to the encoder, that we understood. Key difference, instead of passing only context embeddings to decoder, the hidden states of all input words are passed. Okay. Rather than just passing the context, the hidden state of all the inputs are passed there. Okay. Let's see. Instead of passing only a context embedding to the decoder, the hidden state of all the input words are passed. A state of a word is an internal vector from a hidden layer of an RNN containing information about the previous words. The decoder uses the attention mechanism to look at the entire sequence. Output quality improves significantly because the model now examines the entire sequence using the embeddings for each token rather than a limited context embedding. So basically, as I understood is, it gets more context. Like in the initial approach, if we just use this one, if we just use word to vec, there is no context at all, and then the input is represented as word to vec embeddings, and then the encoder converts it into a context embedding, single context embedding, and then we came to attention mechanism. Single context embedding wasn't giving accurate results enough, so we created like this one, attention mechanism. Attention allows a model to focus on parts of the input sequence that are relevant to one another and amplify their signal. And the RNN with attention mechanism can generate signals for each input word related to the potential output. Improved architecture with attention input is represented using word-to-vec embeddings and passed to the encoder. Key difference, instead of passing only a context embedding to the decoder, the hidden states of all the inputs words are passed. A state for a word is an internal vector from a hidden layer of an RNN containing information about the previous words. The decoder uses the attention mechanism to look at the entire sequence. Output quality improves significantly because the model now examines the entire sequence using the embeddings for each token rather than a limited context embedding. This makes sense. Attention during generation. During generation, the model attends to the most relevant input. So most relevant input means that in that one you can see here, most relevant words are this one, high attention. Okay, during generation, the model attends to the most relevant input. After generating equa1 from input I love llamas, the attention mechanism highlights the most relevant words for the next token. equa1 llamas. Okay. The sequential nature of this RNN architecture prevents parallelization during the model training. The sequential nature of this RNN architecture prevents parallelization during the model training. Got it. So we learned about the attention or encoding and decoding the context with attention in this chapter. Let's move on to the next chapter in just few minutes.
In our previous video,
Let's take a small break before that. Hey, welcome back. Okay, so until now we saw what are like, what is language as a bag of words, and what does it mean by vector embeddings, and how we make it better by providing contextual information in terms of like encoding and decoding context with attention. And now the next step is transformers and then tokenizers. Let's dive into those. So understanding language models with transformers.
In our previous video, we explored the main techniques of attention. In this lesson, you will explore how this technique was further developed and to this day still powers many large language models. The true power of attention and what drives the amazing abilities of most large language models was first explored in the Attention is All You Need paper. This paper introduces the Transformers architecture, which is based solely on attention without the recurrent neural network. This architecture allows the model to be trained in parallel, which speeds up calculation significantly compared to the RNN-based model, which precludes parallelization. Let's explore how this transformer works. Assume you have the same input and output sequences as before. The transformer consists of stacked encoder and decoder blocks. These blocks all have the same attention mechanism that you saw previously. And by stacking these blocks, you amplify the strength of the encoder and decoders. Let's take a closer look at the encoder. The input, I love llamas, is converted to embeddings, but instead of word-to-vec embeddings, we start with random values. Then self-attention, which is attention focused on only the input, processes these embeddings and updates them. These updated embeddings contain more contextualized information as a result of the intention mechanism. They are passed to a feed-forward neural network, which is a similar network that we explored before, to finally create contextualized token word embeddings. Remember that the encoder is meant for representing text and does a good job of generating embeddings. Self-attention is an attention mechanism, and instead of processing two separate sequences, it processes only one sequence, the input, by comparing it to itself. Now, after the encoders are done processing the information, the next step is for the decoder. The decoder can take any previously generated words and pass it to the masked self-attention, similar to the encoder to process these embeddings. Intermediate embeddings are generated and passed to another attention network, together with the embeddings of the encoder. Thus, processing both what has been generated and what you already have. This output is passed to a neural network and finally generates the next word in a sequence. Masked self-attention is similar to self-attention, but removes all values from the upper diagonal. Therefore, it masks future positions, so that any given token can only attend to tokens that came before it. That helps leaking information when generating the output. The original transformer model is an encoder-decoder architecture that serves translation tasks well, but cannot easily be used for other tasks, like text classification. In 2018, a new architecture called bidirectional encoder representations from transformers, or BERT, was introduced that could be leveraged for a wide variety of tasks. BERT is an encoder-only architecture that focuses on representing language and generating contextualized word embeddings. These encoder blocks are the same as we saw before. Self-attention followed by neural networks. The input contains an additional token, the CLS or classification token, which is used as the representation for the entire input. Often we use this CLS token as the input embedding for fine-tuning the model on specific tasks, like classification. To train a BERT-like model, you can use a technique called masked language modeling. You first randomly mask a number of words from your input sequence and have the model predict these masked words. By doing so, the model learns to represent language as it attempts to deconstruct these masked words. Training is typically a two-step approach. First, you apply masked language modeling on large amounts of data, and this is called pre-training. After which, you can fine-tune your pre-trained model on a number of downstream tasks, including classification. Generative models, in contrast, use a different architecture. Assume that you again have another input sequence and randomly initialized embeddings. The input is then passed to the decoders only, as generative models tend to only stack decoders. One of the first implementations is called GPT, or GPT-1. It stands for Generative Pre-trained Transformer, as it uses the Transformer decoder. A decoder block uses again masked self-attention, which is then passed to a neural network. Note that it does not use any encoders as we explored previously. And finally, the next word is generated. These are the two flavors that you will see most often. Generative models, like ChatGPT, and representation models, like embedding models. These models have something in common, called the context length. You start from an input sequence. Tell me something about llamas that we ask of the generative model in this example. Now let's say that you already generated some tokens previously. The original query, together with the previously generated tokens, represent the current context length. That is the amount of tokens that are currently being processed. In contrast, a generative LLM like GPT-1 or even a representation model can have a maximum context length, for example 512. That means that the model can only process 512 tokens at a given time. Note that this also includes the tokens that are being generated as they update the current context length. These generative models do the large and large language models justice. GPT-1 already had more than 100 million parameters. The next version, GPT-2, with over 1 billion parameters, and GPT-3 with already 175 billion parameters. As the number of parameters grew, so did their capabilities. That is why you will often see such large models. Looking back at a year that we playfully call the year of generative AI, it all started with the well-known ChatGPT model, or more accurately, GPT 3.5. Following the success of ChatGPT, many other proprietary models soon followed. And fortunately, open source models followed quickly. These are models that have their weights publicly available for us to use. Some of them can even be freely used for commercial purposes. Let's go to the next lesson and learn about tokens and embeddings.
Okay, so that was a lot to digest. Let's try to summarize. If we don't understand something, let's head to ChatGPT and get the clarification about those topics, and then only let's move ahead. Otherwise, it wouldn't make sense. Let me get my notes ready so that we can go over that. Okay, so why am I there? Let's see. Okay, this one's better. Yeah. So in this segment, we focus on transformer architecture that is introduced in the Attention is All You Need paper and its evolution into modern LLMs. Transformer architecture fundamentals. Key innovation: architecture based solely on the attention mechanism without any recurrent neural networks. and parallelization advantage. Unlike RNN based models, in RNN based models, transformers can be trained in parallel. In RNN based models, we cannot train it in parallel because we need to provide the sequence as the input, already generated sequence as the input for generating the next level output. But here, like here in the transformers, initial transformer architecture, um, that can be trained in parallel as well, significantly speeding up the calculations. Structure consists of stacked encoder and decoder blocks, each using the same attention mechanism. Stacking blocks amplifies the strength of the encoders and decoders. Okay, so parallelization and stacking the blocks together to using the same attention mechanism. Encoder architecture details input text converted to embeddings starting with random values rather than word to vector mechanism. Self-attention mechanism, attention focused only on the input sequence, processing by comparing it to itself. Attention focuses only on the input sequence, processing by comparing to itself. Self-attention updates embeddings to contain more contextualized information. Updated the embeddings pass through feed-forward networks to create final contextualized word token embeddings. And encoders excel at representing text and general quality embeddings. Okay, so the self-attention. Basically, it looks like this. Here, let me capture that. Okay, attention is all you need. So here, input text converted to embeddings starting with random values rather than word to vec. So starting with random values for embeddings here, and then self-attention updates embeddings to contain more contextualized information. Self-attention is the first step. It will update the embeddings to contain more contextualized information. Updated embeddings pass through feed-forward neural network to create final contextualized token or word embeddings. So once it is passed through feed-forward neural networks, it will create the final contextualized token or embeddings. Encoders excel at representing text and generating quality embeddings. Next goes the decoder architecture. So self-attention. Okay, just here they have touched upon the self-attention structure. Okay, so now that is done. Decoder architecture details. Takes previously generated words and pass them to masked self-attention. So pass them to masked self-attention. Okay. What does that mean? I love Llama's self-attention feed-forward neural network. Okay. Similar to the self-attention, but removes values from the okay. I lost my okay. I got back. Okay. Masked self-attention, similar to self-attention, but removes values from the upper diagonal, masking future positions, so tokens can only attend to previous tokens. Okay, did not understand it completely. Masked self-attentions. Okay, masking prevents information leaking during the output generation. Okay, intermediate embeddings process through attention network together with encoder embeddings. Output passed to the neural network generate next word in the sequence. Okay, this was a bit tricky for me, a bit overly complicated for me. Let's see. Let's ask ChatGPT to understand. Okay, Okay. So now let's do one thing. Let's copy this section, decoder architecture, and let's move to ChatGPT. Explain this section in simple words related to the transformer architecture based on attention is all you need. Copying the image. Okay, I have both the images copied and pasted there. Let's see what ChatGPT explains. Okay, has generated something. Let's see. Let's walk through what the decoder section is doing in plain, no mysticism terms, using the picture and attention is all you need as the mental model. What the decoder is actually for. The decoder's job is not to understand the input sequence. That's the encoder's job. Okay. The decoder's job is narrower and harsher. Given what I have already said and what the encoder understood, what word should I say next? Given what I have already said and what the encoder understood, okay, what word should I say next? Everything in the decoder exists to answer that one question safely and causally. Given that what I have already said based on the context of the previously generated output and what the encoder has understood about the context, what word should I say next safely? Okay, everything in the encoder exists to answer that one question safely and causally. Feed in previously generated words. Step 1. The decoder does not see the future sentence. It only sees these are the words I have already generated. In the diagram, that's things like ikhow. Those are turned into embeddings and passed into decoder stack. Okay. Masked self-attention, the crucial trick. This is normal self-attention with one brutal rule. You are not allowed to look ahead. In matrix terms, that's triangular you see in the heat map. Diagonal and left is equal to allowed. Diagonal and left is equal to allowed. Right of the diagonal blocked or future tokens. Basically like this. What's mentioned here. In this one you can see, right, diagonal, and to the left is everything is allowed. The future ones are not allowed. Okay, but that is also still abstract for me. Let's look into that to understand it more intuitively. Okay, this is normal self-attention with one brutal rule. You are not allowed to look ahead. In matrix terms, that's the triangular mask you see in the heat map. Diagonal and left is equal to allowed, right of the diagonal blocked. Why this matters? During the training, the full sentence exists. Without masking, the model would cheat by peeking at the correct future word. Okay. Masking enforces the same rules during the training that exists at inference time. So when predicting the word after ikhow, the word how can attend to ikhow, not van or llamas. This is why cow, not van or llamas. Okay. So when predicting the word ikhav, the token how can attend to only the already predicted words, not to the future words. This is why the attention matrix looks lower triangular instead of the full. Think of it as time travel prevention. Okay. Encoder decoder attention, grounding in the input. After masked self attention, the decoder asks a second question. Given what I have said so far, which part of the input sentence matter? This is encoder attention. Queries comes from the decoder. Keys and values come from the encoder output. This is this is how the decoder stays faithful to the source sentence instead of hallucinating fluently but incorrectly. In translation terms, encoder here's what the source sentence means. Decoder, which parts of the meaning help me pick the next word right now. Okay. Feed forward network. So this is one of the important things. After attention mixes information, past generated words, relevant input tokens, the result goes through position wise feed forward network. Same MLP applied to every position. No sentence magic, no sequence magic here, just non-linear transformation. This step sharpens the representation into something usable for prediction. Predict the next word. Finally, the decoder output is projected into vocabulary. Softmax turns into, okay. Then loop repeats, append, van, mask, okay. The big picture, why this design works. Okay, the decoder is powerful because it combines three constraints: auto regression, only past tokens allowed; attention, flexible context instead of fixed windows; encoder attention keeps outputs tied to the inputs; remove masking and training collapses into cheating. Okay, remove encoder attention and you get fluent nonsense. Remove encoder attention. Okay, remove self attention and long range structure dies. This architecture looks ceremonial on paper, but it's ruthlessly practical. Every component exists to stop the model from lying to itself. Once you see that, the diagram stops looking decorative and starts looking defensive. Okay, now I think you understood you explained the concepts, but this was not like very intuitive for me. Like, can you explain with an example clearly from step one to what the transformer architecture is doing in an intuitive manner? First thing is, let's go simple. Understand that I'm a layman and don't know anything about this one, and go step by step. And then we can go on to the advanced questions if I have. I don't leave out any technical terminologies there, but still I want you to simplify it and explain it in the layman terms. Okay, we'll do like this. You're watching a very fast, very picky translator at work. Okay, I'll keep the real technical terms: token, embedding, attention, query, key or value, softmax, mask, etc. But I'll explain each one in human language as we hit it. And we will walk step by step through an example. Okay, the example we will use: translate Dutch to English. Input is ik hou van llamas, and target output we want is I love llamas. A transformer, the original paper encoder decoder model, does this by encoder reads the whole input and creates meaning vectors. Okay, decoder writes the output one word at a time using mask self attention, look only at the words already written, and encoder decoder attention, look at the input meaning. Okay, and tokenization. Step 0, tokenization. Turn text into pieces. Token a piece of text, often a word is chunk, basically not the exact word as we discussed, but a word is chunk. Ik hou van llamas, this the input decoded to this one. Output tokens will be built gradually, like this: I love llamas. So BOS means beginning of sentence, just the beginning of sentence, and then beginning of sentence plus I, beginning of sentence plus I love, and then henceforward. Okay, embeddings. Turn tokens into vectors. Computers don't hold words, they hold numbers. Embeddings, a learned vector list of numbers representing a token. So each input token becomes a vector. Ik becomes embedding 1, how becomes embedding 2, WAN becomes embedding 3, llamas become embedding 4. Positional encoding. Because attention alone doesn't inherently know order, we add positional encoding so the model knows this token is first, second, and third. Okay. So the encoder actually uses this one. Okay, because attention alone doesn't inherently knows order, we add positional encoding so the model knows this token is first, second. Okay. So the encoder actually uses x1 is equal to e1 plus p1, x2 is equal to e1 plus p2. P2 is positional encoding. That's straight from the paper's idea. Token meaning is token meaning plus position. So e1 contains, this embedding contains the token meaning, and p1 contains the position. So that is for the first word, ik. And for how, it is contained in e2 or embedding 2, and then positional embedding 2. So x3, x4. So it is actually converted into this one. That's straightly from the paper's idea, token meaning plus position. So this is the first step. Step 1, embeddings. Turn token into vectors. So it is converted into vectors which contains the meaning plus the position. Okay, next, encoders self-attention. Okay, input words talk to each other. Here's the intuition. The encoder takes each input word and asks which other input words help me understand this word. Okay, that's self-attention. The scary but simple QKV idea. What is QKV? Query key value idea. For each position, the model makes 3 vectors. For each position, the model makes 3 vectors. Query, what I am looking for. Key, what I contain. Value, the information I provide if selected. Okay. Then it scores how much each word should pay attention to others. Okay. Example intuition. For how uh, or love, it should attend strongly to ik. Subject, it should attend strongly to ik, and maybe llama's object to understand the relation. Okay. Example intuition. For how, it should attend strongly to ik. Okay. Then it scores how much each word should pay attention to others. For how, it should strongly to ik, and maybe llamas to understand the relation. Okay. The output of the encoder is a set of new vectors, one per input token. Okay. H1, H2, H3, H4. These are contextualized embeddings. Each one now contains info from the whole sentence. Okay. Now in this one, scores how much each word should pay attention to others in the sentence. These are contextualized embeddings. Each one now contains info from the whole sentence. Think of H as a memory of the input sentence stored as vectors. Okay. So it is providing the context in the context of the input words according to each other. Basically, it is self-attention. Okay, encoder self-attention. Input words talk to each other. Got it. And decoder starts generating one token at a time. Now the decoder writes English. Step 3.1, start with what we already have. At time t is equal to 1, we have only BOS, means beginning of sentence. Decoder turns BOS into embedding plus positional encoding 2. Okay, that's the beginning sentence or beginning of the sentence. And then masked self-attention, no peeking into the future. Step 4, masked self-attention, no peeking into the future. This is the part from your diagram. Okay, so as I showed there, it was only a diagonal, and only we have access to below the diagonal, not above the diagonal. Okay, in the decoder, self-attention is masked, meaning when predicting the next word, the decoder can only look at earlier generated word tokens. When predicting the next word, the decoder can look into earlier generated tokens. It cannot look at future tokens because they don't exist yet in real use. So when the sentence is BOS I love and it's computing the representation for love, it may attend beginning of sentence I love, but not the words after love. Why the triangle mask? Because attention is a big who looks at whom table. Because attention is a big who looks at whom table. Masking sets the look ahead entries to negative infinity before softmax, so their probability becomes 0. Masking sets the look ahead entries to negative infinity before softmax, so their probability becomes 0. That's why you see the upper triangle blocked, because attention is a big who looks at whom table. Okay. Encoder decoder attention. Decoder looks at the input. After masked self attention, the decoder now asks, given what I have generated so far, which part of the input sentence memory matter right now? Which part of the input sentence memory matters right now? This is called cross attention or encoder decoder attention. Mechanically, decoder provides queries, what it needs. Encoder provides key or values, what input contains. Intuition. When the decoder is about to generate I, it should focus on ik. When about to generate love, focus on how. When about to generate llamas, focus on llamas. This is the alignment behavior you often see in translation. Feed forward network per position thinking. After attention mixing, each position goes through a feed forward network. Same small neural network applied to each token position independently. Add nonlinearity and capacity. Adds nonlinearity and capacity. Intuition. Attention decides what information to gather. FFN decides how to transform or use it. Vocabulary injection plus softmax chooses the next word. Now we have vector representing what the next word should be, and transformer converts that vector into scores of every word into vocabulary. I 9.2, the minus 1.7, love 4.1. Softmax turns scores into probability that sum to 1. Then it picks a word. Greedy max probability or sampling beam batch. So basically whichever is the highest probability word, it will pick that. Let's say it picks I. Now the output sentence becomes beginning of sentence and then I. Repeat the whole decoder process again to get the next word. Walk the full generation loop. Super concrete. Decoder has BOS, mass self attention only, BOS. Cross attention looks at the encoder memory for what starts the sentence. Ik predicts I. Generate word 2. Decoder has BOS, mask at self attention I can look at BOS and I, and cross attention. Now it focus on how. Predicts love. Generated word 3. Generate word 3. Decoder has BOS I love, mask self attention love can look at BOS and I love, and okay, focus on llamas. That predicts llamas. So that is focusing on that particular word. Generate the end token, end of sentence, and stops. Final output, okay. The core intuition, one sentence. The encoder builds meaning memory of the encoder builds a meaning memory of the input, and decoder writes the output left to right using mask self attention to stay consistent with what it already wrote, cross attention to stay faithful to the input. Okay, I think this makes sense now. Let's move on to I think it's a good time to move on to the next chapter. I think we didn't cover the nodes completely. Let's go back there. Okay, and then here, so now this decoder architecture is over, and then BERT, encoder only architecture. BERT released in 2018 bidirectional encoder representations from transformers, and the purpose is designed for representing the language and generating the contextualized word embeddings. Can be leveraged for a wide variety of tasks, including the text classifications. CLS, special classification token added to input, used as representation for entire input sequence. CLS token commonly used as input embeddings for fine-tuning model on specific tasks. BERT training approach, masked language modeling training techniques where words are randomly asked from a input sentence. Models learn to predict the masked words, okay, thereby learning to represent the language. Two-step training process. Pre-training, apply masked language modeling on large amounts of data. Fine-tuning, adopt pre-training model for downstream tasks like classification. And GPT, decoder-only architecture. This is a decoder-only architecture. GPT-1, first impressions or first implementation standing for generative pre-trained transformer. Uses only decoder blocks from transformer architecture. Architecture, decoder blocks uses masked self-attention followed by neural network. Does not use encoders like the original transformer. Designed specifically for text generation tasks. Model type comparison, generative models. Example includes ChatGPT, GPT series focused on text generation. Representation models, examples include BERT and embedding models focused on creating numerical representation. Content length explained. Current context length, amount of tokens currently being processed, including original query and previously generated tokens. Okay, amount of tokens currently being processed. Okay, that is the current context length. Models have limits on how many tokens they can process at once. Example, GPT-1 or representation models might have context length of 512 tokens. Generated tokens count towards and update the current context length. Okay, model scale evolution over 100 million parameters, GPT-1. GPT-2, we saw Llama is 70 billion parameters, I guess. It is over 1 billion parameter GPT-2. GPT-3 became bigger than Llama, Llama 2. 175 billion parameter. As parameter count grew, model capabilities expanded significantly. The rise of generative AI 2023 highlighted as year of generative AI started with ChatGPT, and I think there is a good representation for the same. Yeah, started with ChatGPT, followed by ChatGPT success. Many proprietary models emerged, open source models with public available weights soon followed, like Llama, and also I think DeepSeek. Some open source model can be freely used for commercial purposes as well. So that's mostly about the transformers. Let's dive deep into tokenizers for now, and let's look into some of the code examples. So
In the last lesson, you learned how word meaning was represented in vectors. We briefly introduced tokens as words or word pieces. In this lesson, we will illustrate what those are and how they help.
just give me a second. Okay, so let's move on to next section now.
In the last lesson, you learned how word meaning was represented in
vectors. We briefly introduced tokens as words or word pieces. In this lesson, we will illustrate what those are and how they help transformers do their jobs. If you're already familiar with tokens and tokenizers, you can skip this lesson. Otherwise, let's take a look. Imagine you have a given input sentence like have the Barts who. For a language model to process that input text, it will first break down the text into smaller pieces. Each piece is called a token. This process of breaking down the text is called tokenization. Each token is then turned into a numerical representation, also called embeddings. These are vector values that represent the semantic nature of a given text. These embeddings are static, and each embedding is created independent from all other embeddings and tokens. These embeddings are processed by the large language model. and converted into contextualized embeddings. These contextualized embeddings are still one for each input token, but have been processed such that all other tokens are considered. These embeddings can be the output of a model, but also used by the model to then create the output. In the case of generative models, this can be another token. Let's explore in detail how this tokenization process works. Given an input sentence, have the bars who, it's tokenized or encoded into smaller pieces. Tokens can be entire words or pieces of a word. When these pieces are combined, they form the original word. This process is necessary as tokenizers have a limited number of tokens or vocabulary. So whenever it encounters an unknown word, it can still represent it by these subtokens. Each token has an associated fixed ID to easily encode and decode the tokens. These are fed to the language model that internally creates the token embeddings. The output of a generative model would then be another token ID, which is decoded to represent an actual token or word. There are many different tokenization levels that we can explore. Assume you have an input, have the bars who precede it, together with a special symbol. When you represent this input as word tokens, the entire sequence is represented by words. Subword tokens, the example that we saw previously, can either be the entire word itself or subpieces of the original word. If the tokenizer does not have a token for bards, it can still represent it with its tokens for B and arts. You can split subword tokens into character tokens, one for each character in the original word, representing the entire input as nothing more than each individual character. The smallest representation is that of bytes, which is used to encode a single character of text in a computer. This is done for every single character. Note how the symbol needs additional bytes for representation, as that symbol is more complex than just a single character representation. In practice, most large language models have tokenizers that work on a subword token level. Its vocabulary is flexible and allows to represent most words by either its entire representation or using subtokens. Let's now move to the notebook to explore different tokenizers. To explore different tokenizers, we first need to install the transformer package with pip install transformers. This is used not only to interact with tokenizers, but also to use large language models. Since I've already installed it in my environment, I can go ahead and skip it. Next, let's explore how this tokenization process works. To do so, and to load your tokenizer, you will first need to import the auto tokenizer from transformers. And this is used to interact with any tokenizer. Then you can choose any sentence to process. For this example, I selected the well-known Hello World example as the sentence to process. The tokenizer that you will be using is called the BERT-based case model, and it's a pre-trained encoder model which is named BERT. Now that we have loaded in our tokenizer, we can start processing our input sentence. You can use the tokenizer to process the input sentence and extract token IDs. You can then print the token IDs to see what this variable contains. Note how it contains a bunch of numerical values, and it's unclear what they represent exactly. As we saw before, token IDs represent certain tokens, but to get those tokens, we first need to decode them. And you can decode these tokens with the decode function that the tokenizer has. So when you loop over the token IDs, you can decode each token and print it. Note how you will now see 5 tokens represented. The sentence Hello World starts with the CLS token. The CLS token, or the classification token that we explored previously, represents the entire input. Then you have tokens for hello, world, exclamation mark. And there's also the special character sep. It's the separation token and signifies the end of a sentence. To visualize all these different tokenizers, you will need some special code. Before you create your function, first you will create this list of colors. These are RGB colors that we will use to highlight the tokens that help you differentiate different tokens. You can use any colors, these are selected for you. Then the main function, and it's called show tokens. And show tokens is what allows you to separate each token by color. It takes in a sentence and a name. The sentence of the sentence that you want to process and the name of the tokenizer that you want to load in. You load in the tokenizer in the same way that you've done before. You choose a name for the tokenizer that you want to process, and then you create token IDs. Those were the IDs that you saw before, those numerical values that need to be decoded before it's clear what words and tokens they actually represent. We will extract the vocabulary length because it's also interesting to see how vocabulary might differ between tokenizers. Then each token will be printed through decoding with the tokenizer that we've explored before, and each token will be highlighted. And this highlighting procedure allows you to easily differentiate between techniques that different tokenizers use. Before you will use this function, let me first introduce the text that you will be using. This text contains all different types of words to showcase how these tokenizers will process this particular input. Note that we have words that are fully capitalized, that we have values in there, and that we even have special symbols to see what the tokenizer will do when faced with this particular sequence. Let's explore the tokenizer that you used before in more detail. We can do that using the show tokens function that you created before, and you pass it the input text. After you run it, you will see two pieces of information. First, the vocabulary length of this tokenizer. It shows a value of almost 30,000, which means that this tokenizer has almost 30,000 values or tokens it can represent. Below that, you will see all the tokens that it used for representing your input text. As we explored before, it starts with the CLS token, the classification token, to showcase or to represent the entire input. This tokenizer has a lot of difficulty representing the word capitalization. Note how it has to break that down into many tokens before it can actually represent that word. Those hashtags showcase that this token belongs to the token before that, and that together they represent a single word. You will also see the UNK token appearing up in these tokens. It's the unknown token and is used when it simply doesn't know how to represent any token. Next, let's see how a more recent tokenizer differs from this BERT model. We will this time use the GPT-4 tokenizer. It's called tick token, and although we cannot access the GPT-4 model itself because it's proprietary, the tokenizer is still available. And you can run this. What you will see is a vocabulary length that's more than 3 times as large as the BERT model that you explored previously, with 100,000 tokens. It needs to use fewer tokens to represent the inputs. Capitalization is now only 2 tokens. And this model, this tokenizer, is meant for a generative representation. So it doesn't have the CLS and the SEP classification tokens or those special characters. It's interesting to see how it needs fewer tokens to represent this entire input. Even the tabs, it represents that very well. Because this model has such a large vocabulary length, it's easier to represent uncommon tokens. But there's a trade-off. The larger the vocabulary length is, the more embeddings need to be calculated for each of those tokens. So there's a trade-off between choosing a tokenizer with potentially a length of 1,000,000 tokens and actually learning the representations for each of those tokens. Now, many of the models can be found online on the Hugging Face platform. There you will find much of the tokenizers to use, and because tokenizers themselves are relatively small, it's easy for you to try them out. See how they differ, what changes you have between tokenizers that are for Western languages or for Eastern languages. In the next videos, Jay will explain to you how large language models process tokens to generate text.
Okay, here it was a detailed explanation about tokenization, and also he explained with code like how the tokens are represented and how it is split between in this program, and what the tokenization vocabulary consists of in different models. And based on that, like here for example, in the show tokens, in this method the tokenizer name is also passed as a parameter. So based on the tokenizer that we pass, so it varies like how many words are there in the vocabulary and how easy is it to represent those words in the based on the vocabulary. For example, that this word especially, this is the input that we used, capitalization, using bird-based case models. Like it was finding it hard to represent that word. It was going to cap I, T and L as a separate token and everything. I think when they used uh, GPT-4, it went to capital and ization as two different tokens, only that's it. But it had unknown for these two symbols. um, yeah, so uh, it just gives us a good mental model about like how the tokenization is happening underneath and how these words are being represented in those models. So let me refresh this once again. Yeah, you can see here, A is the new electricity. Okay, yeah, let's read this one entirely. In this notebook of lesson 2, you will work with several tokenizers associated with different LLMs and explore how each tokenizer approaches tokenization differently. Yeah, as I mentioned. We start with setting up the lab by installing the Transformers library and ignoring the messages. Let's copy this one entirely to our nodes. Okay, click on File option at the top of the menu of the notebook and click on Download As. Select Notebook. Okay, let's try that one. Download as ipy notebook .ipy notebook .ipy notebook. Okay, now, okay, this is the notebook that we have locally. Let's go to Jupyter notebooks. Okay, and try it. Jupyter Lab. This is the latest web-based interactive development environment, the original web application for creating and sharing computational documents. So let's go to this one, Jupyter Notebook, the original one. Okay, we need to have our own account and keep a track of everything that we create, like our GitHub. I've been losing my Jupyter Notebook previous histories. Okay, I don't know if I have my account here. Let me see. It's redirecting to Jupyter Lab. That is good. Let's go back here. Okay, there are some examples which are useful. I think I'll definitely come back to this and have a complete session about Jupyter notebooks. So that would be a good, that would provide a good fluency when I'm dealing with these labs or anything. So now file, there was an export option, so there must be an import option as well. New notebook. Mm. I want to import one. So file, open from URL, open console for notebook, save, duplicate, reload notebook from disk, download, save. Okay, upload. Okay, I just selected something. Are you guys able to see it? Okay, in this notebook, let's read it from here. In this notebook, okay, we start with setting up the lab by installing the transformers. What is this button? Let's just click it once and see. Okay, that is my Speechify plugin. So I forgot I had it since I haven't used it for a long time. Okay, let's disable that for now. Don't need it. Okay. Okay, we start with setting up the lab by installing the Transformers library and ignoring the warnings. The requirements for this lab are already installed, so you don't need to uncomment the following cell. If install Transformers greater than or equal to this one. Okay. From Transformers, import or auto tokenizers. Sentence hello world tokenizer auto tokenizer dot from pre-trained this one token.id print this one. Now how to execute this first thing. Let's run it and see. Token IDs, cell in one for ID in token IDs, so that is not defined, so we need to execute it one by one. From transformers, okay, module not found, we don't have the transformer. Okay, we need to install the transformers. How to execute this? Does anybody know? Okay, it's not working here. Access requirement.txt file. If you would like to access the requirements file, click on the file options on the top of the menu in the notebook, then click open for more. Okay, let's go back there. Okay, let's execute from here for now. Okay. Okay, then run this. Okay, sentence hello world tokenizer be tokenizer config.json config.json vocabulary.text and tokenizer.json. So everything is loaded. Now we are done. Token IDs tokenizer.sentence. Now we got the token IDs. Now it should print. Time for test. Okay, it printed all the tokens here. You can see. Okay, now it is working. Let's see. We have this Jupyter. So I'll have another live stream where we will go through all the Jupyter notebooks, or we will have a Jupyter notebook kind of end-to-end session. But for now, let's try to execute this one. So we have the hello world and all this, and we have the token IDs separated from the input IDs. We have the tokenizer. We have used the tokenizer bird based cased, and then for this hello world, we got these many tokens, 5 tokens or 5 token IDs. So let's see what are those token IDs by decoding them one by one. So the tokens that is emitted is in the numerical format. So let's decode those by using the same tokenizer. We know the tokenizer, which tokenizer it is, auto tokenizer from pre-trained this one. So using the same tokenizer, I'm decoding it. So let's see. Okay, it provided CLS classification token, hello world, and then this exclamation as one separate token, and then ACP. I forgot what it is. You can comment there if you remember exactly what token is ACP. Okay, in this next section, you will wrap the code of the previous section in the function show tokens, basically. Show tokens. The function takes in a text and model name and prints the vocabulary length of the tokenizer and a colored list of tokens. Basically, it's doing what we did here one by one, everything in the single program, but it is printing the tokens in a different color index, okay, length of colors. And then it is also, we are emitting the vocabulary length here for the tokenizer, length of the tokenizer basically. Okay, and enumerate tokenizer.decode. Okay, same thing. Okay, let's run this one. So nothing, it just we defined the method to print tokens or show tokens. Now we have this text. So let's run this to load the text. Now we can run the text using different tokenization methods. So bird base cased and bird this one and GPT-4 and all this. Let's run this one and see. First thing, so as they explained, for English CA, for this is the text here. So for this one, you can see how much there are limited number of vocabulary length, 28,996. So they might not have capital and ization as separate ones. So they have only CA, PI, TA, and ICAT. So, but it is able to come up with the split of tokens for capitalizations with this complex format, and then unknown for these special characters. And then you can see show underscore token, and S as a separate one. False if there is no false if, ALS and E, and then none as a character, none has a token actually, EL has a token, if has a token, and equals is a separate token. So all these things. Let's see for the bird base uncased. Let's focus mostly on this capitalization, how this one is tokenized. So this one was bird base cased. This one is bird base uncased. Let's run this one. So here also you can see there is slight improvement, capitalization, but uncased. And the number of tokens here, let's see the number of tokens. Okay, 30,522. Here 28,996. But this doesn't have the separation of lowercase and uppercase. So this one was capitalization like this, but it split into tokens and show and saved it, represented it in the lowercase letters only. And then as usual, these ones are unknowns and everything else is kind of not that interesting. So we can go to GPT-4 now and see the difference in vocabulary length and also how the capitalization is represented. So in GPT-4 now, okay, in GPT-4, let's see. Okay, now we can see here capital and ization are represented as two tokens and with the appropriate case as well. So it was represented in capital. And then here English also camel case you can see here, but here English was lowercase. But another thing is the main significant difference that should be noticed is the vocabulary length was 30,000 tokens here, and here over 100k 100,000 tokens, and the same thing the first one used 28,990 almost 29,000 tokens. Yeah, so that difference makes up for it. Like we are able to represent it as it is without much confusion. You can also explore the tokenization strategy for the other models. The following is suggested list. Make sure you consider the following features when you are doing your comparisons. Vocabulary length, yeah, that is something which we need to see. Special tokens and tokenization of the tabs, special characters, and special keywords. Let's see GPT-2. Okay, so 50,000 tokens capitalization is cap, ital, ice, and ization. So English and nothing for the special tokens. Here, tokenization of the tab. That was interesting. 2 tabs. Okay, 2 tabs. Where it is in the text. 2 tabs. Okay. Oh, after that 2 tabs, it is 2 tabs. 2 tabs, and then tab is represented by a token here. Okay, 3 tabs. 3 tabs are represented by another different types of token here. So here, in the old one, 2 tabs and then percent and then 2 tab S, and then it was the space was not even represented. It represented only the codes but no tabs in between. But here you can see tabs, and then it represented the tab in 3 tabs in the GPT-4. And then in GPT-2 as well, we have the 3 tabs. Okay, there's nothing for 3 tabs actually, or probably this one. Yeah, 3 tabs are represented by 6 different tokens, and 2 tabs are represented by 3 different tokens here. So yeah, let's see Google Flan T5 small. This is another tokenizer. Capitalization unknown. Most of these ones are unknown, and then tokenization false. Okay, 2 tabs and 3 tabs. Nothing for tabs as of here. And let's run the star coders. No stark difference for me. Capitalization here, vocabulary 49,000. It was 32,000. Since it is like wherever I'm seeing more vocabulary length, I'm seeing at least the capitalization is easily represented in those ones. And for 3 tabs also, you can see there is a different token, and 2 tabs there is a different token. And let's run one more, and this one has a vocabulary length of 32,000. So you can see the difficulty in representing capitalization, and then there's no separate. Oh, there is a representation for 2 tabs and 3 tabs. Finally, Quen, we will run with Quen tokenization. Okay, we can see, okay, this is the highest vocabulary length, 151,665 here. So this is represented easily, and you can see that the special character is also represented here for the first one. So this music symbol icon, this is represented. Show tokens. Okay, underscore tokens is one thing. False is represented clearly, and yeah, 2 tabs is represented, 3 tabs are represented. Yeah, this is much more progress than the other ones. Let's look into my notes once again, just to revise once if I'm missing something, and then we can proceed on to move on to the next chapter. Okay. Tokenizations in Transformer LLMs. So this lesson focused on tokens and tokenization, how text is broken down for small spoken down for processing by language models, intended for those unfamiliar with tokens and tokenizers. Experienced viewers could skip it. Okay, practical demonstrations provided using the transformer package. So we saw that in the Jupyter notebook. And then tokenization process explained, breaking down the text. Language models first break the input text into smaller pieces called tokens. Token definition: a token can be an entire word or a piece of a word. Each token is converted into numerical representation that captures semantic meaning. Initial embeddings are static and created independently for each token. Contextualized embeddings: large language models process static embeddings to create contextualized embeddings that consider all other tokens. Why tokenization uses subtokens? Tokenizers have limited vocabulary. So subtokens, we mentioned that it has a limited vocabulary. For example, uh, we cannot have the separate tokenization for capitalization, tokenization. We cannot have separate tokens for all those things. So it's easier if we have the token for token, and ization can be a common one, and we can have a separate token for capital, or maybe um, refrigerate or anything. Ization can follow after that as a separate token. So it is represented as a general token. So that's why we resort to having subtokens that form the original word. Each token has a fixed ID for easy encoding and decoding. Output from the generative models is a token ID that gets decoded back to text. Tokenization levels: word tokens, entire sequence represented by complete words. Subtokens, we saw this one. Most common practice in and can be the entire words or word fragments. Example: parts might split into P and art. Yeah, arts, a full word is not in the vocabulary. Character tokens: one token for each individual character. Byte tokens: smallest representation encoding single characters as bytes. Complex symbols require multiple bytes for a representation. Most modern large language models use subword level tokenization for flexibility. And here, practical demonstration with the transformer package that we saw in the library there, and special tokens using BART, in tokens in BART, CLS token, classification token representing the entire input sequence. So CLS token represents the entire input sequence. SCP token, separation token signifying the end of sentence. Okay. So we had confusion about this one. Hello World example produced 5 tokens including these characters. And visualization function custom. Okay, we saw the show tokens and color highlighting for different tokens there. Displays vocabulary length, and then we saw how it behaved based on different vocabulary length for different tokens. How the representation was different for mainly for capitalization and the special symbols and the tabs. So that's mostly about it. Resources for exploration: many tokenizers are available on Hugging Face platform. Tokenizers are relatively small and easy to implement with. Okay, we can explore different differences between tokenizers for Western versus. Okay, so that's good. Let's get back to our this one, our course, and next thing is architectural overview. So that should provide a bigger picture overview for transformer, and then yeah, there are more things to cover here. Let's see. Let's get back here. Give me give me a minute. I'll just take a break, and we'll be back in a minute or less than a minute. Okay, I realized that all the while I was muted. So I think let's do one thing. Let's go through the section again. Let's start the section architectural overview.
So far, you have learned how language is represented numerically and how words are converted into tokens and dense embeddings. Now you're ready to dive into the details of a transform. When we're thinking about transformer large language models, we know that there's an input prompt to the model, and then there's a generation or an output text that the model generates. Now, one of the first important intuitions to get before sort of understanding how the transformer works is to understand that it generates tokens one by one. So to generate that output that we saw in the previous one, you can see that the model is generating them one token at a time. We'll break down these generation steps so you can understand the underlying mechanisms of how this works. The transformer is made up of three major components. We've already looked at one in the previous lessons. So we've looked at the tokenizer. That is the component that breaks down the text into multiple chunks. And then the output of that tokenizer goes to a stack of transformer blocks. This is where the vast majority of computing is. These are the neural networks that operate on this and do pretty much all the magic that happens here. And by the end of these couple of lessons, you'll see that it's no magic and it's quite understandable what they actually do within a sense. The output of this stack of transformer blocks goes into a neural network called the language modeling head. Let's look at each of these components. We looked at the tokenizer, and we know by now that the tokenizer has a vocabulary that breaks down, it has independent chunks. Let's say we have this vocabulary of 50,000 tokens that this tokenizer knows. The model has associated token embeddings for each of these tokens. So if we have 50,000 tokens in our vocabulary, the model has 50,000 vectors that represent each of these tokens. And these are substituted in the beginning once the model is processing its inputs as it's supposed to. We'll talk about transformer blocks in the next lesson, but let's go over the language modeling head as we're looking at the high level overview here. So at the very end of the processing of a language model, you have all of your tokens that you sort of started with that are defined in the tokenizer. What happens at the end is a kind of scoring or a token probability calculation based on all of the processing that the model in this stack of transformers have done to make sense of the input context and what is requested, let's say in the prompt, and what the next token should be in response to that. And so the result of the language modeling head is this sort of token probability scoring that says, okay, all the tokens that I know, this is how much percent of probability each of these tokens has. And all of these, they have to add up to, let's say, 100%. And so if you have the word deer scored at 40% probability, that becomes the highest probability token that becomes possibly the output, not necessarily the output. But you can choose the highest probability token, and that's one method of choosing the next or the output token. These are called decoding strategies. If you're choosing the top scoring token all the time, it's a good strategy for a lot of cases. It is what happens when you set the temperature parameter to 0. It is a method called greedy decoding, but it's not the only method out there. There are others like top P, for example, that incorporate multiple tokens. So it might generate deer, but also in some cases with lower probability, it might pick the next highest probability token. It definitely looks at the scoring, but it doesn't always have to pick the top one. And these are sometimes important to generate text that sounds natural. And it's sometimes why, when you generate multiple times using the same prompt, you will get different answers. That's all related to decoding strategies, especially if you set temperature to values more than 0. Another important idea or intuition about transformers, and this is one of the ideas that make transformers operate a lot better than previous methods like RNNs, is that they process all of their input tokens in parallel. That parallelization makes it time efficient, let's say. So you can compute a long context, a lot of different GPUs in a single time. The way to envision this is to think of multiple tracks flowing through this stack of transformer blocks. And the number of tracks here is the context size of the model. So if a model, for example, has a context size of 16,000 tokens, it can process 16,000 tokens at the same time. The generated token in decoder LLM transformers is the output of the final token in the model. And we will see in the next slide how generating every other token after you start with, let's say, the first step that processes the input is a little bit different. So here you can see that all of these arrows are red, but then once we generated our first token, now we feed that entire prompt with the token that we've generated into the transformer again. So you can think of it as a loop. It is a loop. And then where you process the inputs one by one as you generate these tokens. One thing that is different between that first step and the second step is that you can cache these calculations because they're going to be exactly the same calculation. And you can cache them to speed up the generation of the model. This is what is called KV caching. Well, K means keys, V is values. We'll talk about these when we talk about attention in the next lessons. So that is one of the major additions to transformers that make them faster. We can also think about metrics. So if you're working with efficiency, there's this metric of time to first token. That is what happens here. So time to first tokens is how long the model takes to process all of this. And then generating every other token is slightly a different process.
Okay. I think I'll try to generate a brief summary or provide a brief summary about this section. So here, let me move to my notes. I don't know if you are able to see the same screen as me. Okay. Okay, it's simple. Here, let's come to this one. So in token generation process, language models generate output tokens sequentially, one token at a time. That we understood. Each generation step builds upon the previous tokens to produce the next token in the sequence. After generating the first token, the entire prompt plus the generated token is fed back into the transformer in a loop. That's how we generate each and every individual tokens. So the in the transformer token architecture, roughly based the transformer can be viewed like this. I will say I think we have a very good visualization there to represent it. So three major blocks are like this. Okay, three major blocks are tokenizer, transformer blocks, and LM head. LM head is language modeling head, I think. Language modeling head, yeah. Tokenizer is the one which breaks down the text into chunks previously covered in the earlier lessons. And stack of transformer blocks contains the neural network. This is a little bit complicated. Contains the neural network where the majority of the computation occurs and performs the core processing of the tokens. Like once tokenizer splits the input into tokens, so this will perform the calculations. And then language modeling head, that is a neural network at the end of the at the end that produces the final token predictions. Basically, when it comes to this one, like it produces the predictions. For example, like for the next prediction or the next letter can be something like this one. Like I'm saying, okay, like this. After the tokenizer processes and the stack of transformer block processes, the language modeling head produces the output in this probability or in this format where it will show different tokens and their probability to become the next token. So here deer would be the first token. That's what it is saying. The probability of this is 40%. But how to detect that probability or which one to be selected, that there are different strategies for that one. Token embeddings and vocabulary. The token has a vocabulary, 50,000 tokens with independent chunks. Each token is in the vocabulary has associated embedding vector. Each token in the vocabulary has an associated embedding vector. These token embeddings are substituted at the beginning when the model processes the inputs. Okay. And next thing is also it was mentioned like when the temperature is great, temperature is 0, it just plainly select based on the greedy approach, whichever has the highest probability it will select that. When the temperature becomes greater than 0, then it will add some randomness, like it might select not just the highest probability ones but the other ones as well. That's why there is a probability of getting different outputs for the same input when we passed into a language model. So let's see that one here. The language modeling and decoding strategies. The language modeling head performs token probability scoring based on all the processing done by the transformer blocks. Okay, the language modeling head generates this probability based on all the processing that's done in this transformer blocks. It calculates the probability percentage for all the tokens in the vocabulary, which must sum to 100%. Yeah, that is given. And greedy decoding is always select the highest probability token used when the temperature is set to 0. Other strategies, methods like top P incorporate multiple tokens and may select lower probability tokens also to generate more natural sounding text. So when the temperature is not set to 0, this can happen. Setting temperature above 0 enables variation in outputs, which is why the same prompt can produce different responses. That's what they mentioned. Parallel processing. So this is another advantage of transformers. Transformer processes all input tokens in parallel, which is a key advantage over previous methods like RNNs, where it was like it could not, it had to generate sequentially. This parallelization enables time efficient computations across multiple GPUs. So obviously parallelization makes it efficient. The number of tokens that can be processed simultaneously is limited by the model's context size. Okay, you can see whenever you see the specifications of each models, like example 16,000 tokens or anything. If you open even cursor today, it will say for each model the number of tokens as the context size. So the number of tokens that can be processed simultaneously is limited by the model's context size. In decoder LLMs, the generated token is the output of the final token position. Decoder LLMs, the generated token is the output of the final token position. Okay, what is this one? Decoder LLMs, the generated token is the output of the final token position. I did not understand that clearly, but yeah, let's see. Okay, this can be visualized like this basically. Uh, all this process. So we have an input and it goes through all this process, and then we have a cached strategy as well. So there is a optimization KV caching here. Like we are processing the almost the same input, right? Like except the like deer is being fed back as an input here. Like this is the first generated output, and that is fed back as an input, and then it will generate a new token as an output. So in the decoder LLMs, the generated token is the output of the final token position. Okay. The generated token in decoder LLM transformer is the output. We will see the next slide how generating every other token after you start with, let's say, okay, let's see that one later. But let's talk about the optimization here, the KB caching. After the first token is generated, subsequent calculations can be cached because they remain the same. Basically, for the almost the same input, the subsequent calculations can be reused. This caching mechanism called KB caching speeds up the token generation as well. So this is good. This is intuitive, easy to understand. Let's move on to the next section now. Okay, so here the transformer block.
In the architectural overview of the transformer, you have learned that after tokenization, the token embeddings are passed through a stack of transformer blocks. Let's get into the details of those blocks. Let's look at a basic example. Let's say we have this prompt, 2 words, the Shawshank. To understand how transformer blocks operate, let's think about the 2 tracks that are flowing through the stack of transformer blocks. In the beginning, our tokenizer has broken down the prompt into these 2 tokens. So the is its own token and Shawshank is the second token. And then since we have the associated embeddings vectors for each of these, we just replace them. And that is what we start calculating. Now we have turned language into numbers and we can apply a lot of interesting calculus on them to predict what the next word is. So the processing that has happened in the transformer block in its components that we'll address here. But before we get into that, understanding this general flow through the model is useful. And so the same thing happens now with the second transformer block that operates on the outputs of the first transformer block in parallel across the various tracks. And this happens down the list of transformer blocks all the way to the end. And then the final layer, this vector, let's say, for the final token in the prompt is presented to the language modeling head, which then outputs or generates the predicted next token. So this is the flow. So
Hi, pardon. Let's go back there. I kind of zoned out there.
in the architectural overview of the transformer, you have learned that after tokenization, the token embeddings are passed through a stack of transformer blocks. Let's get into the details of those blocks. Let's look at a basic example. Let's say we have this prompt, 2 words, the Shawshank. To understand how transformer blocks operate, let's think about the 2 tracks that are flowing through the stack of transformer blocks. In the beginning, our tokenizer has broken down the prompt into these 2 tokens. So the is its own token and Shawshank is the second token. And then since we have the associated embeddings vectors for each of these, we just replace them. And that is what we start calculating. Now we have turned language into numbers and we can apply a lot of interesting calculus on them to predict what the next word is. So those flow to the first transformer block, which generates a vector of the same size as its output. But something has happened in the middle. There's some processing that has happened in the transformer block in its components that we'll address here. But before we get into that, understanding this general flow through the model is useful. And so the same thing happens now with the second transformer block that operates on the outputs of the first transformer block in parallel across the various tracks. And this happens down the list of transformer blocks all the way to the end. And then the final layer, this vector, let's say, for the final token in the prompt is presented to the language modeling head, which then outputs or generates the predicted next token. So this is the flow. So everything flows from the beginning towards the end one direction from the tokenizer down the transformer blocks, one by one, in sequence up until the language model. The transformer.
Okay, this is what they meant uh, in this sentence. Let's go back here. So here in the last section, we saw in decoder LLMs, the generated token is the output of the final token position. So that means, let's go back to this one. So there are each token position that are going through the transformer blocks, but the generated output of the final token position would be the next token. So basically, once we feed the, let's say the shashank, that itself is the phrase or the input, then the next one, redemption or whatever it will generate. So that will be the that will be generated after this shashank. Whatever is generated after this initial token won't be considered as the next token, but whatever is generated as the next token after the last token in this input will be considered as the next token. That's what they mean. Okay, let's go ahead.
The transformer block itself is made up of two major components: the self-attention layer and the feed-forward neural network layer. The feed-forward neural network layer is for a high-level intuition of the feed-forward neural network. If the transformer block only had this, it didn't have attention, it would be able to generate this completion, to say the token that is most probable to come after the Shawshank would be redemption. And so this is in reference to the famous film, because if you look at the training data set, if you get data from the internet or Wikipedia, redemption would be the word that often statistically appears after the Shawshank in most cases. This is one thing that the feed-forward neural network is able to do. So we can think of it as a storage of information and statistics of, let's say, the next word that comes in after the input token. That's a high-level intuition. Like a lot of these neural networks do things that are a little bit more complicated, but this is the reasonable first approach of how to think about the feed-forward neural network. And this contrasts it with self-attention that we'll look at after we finish talking about the feed-forward neural network. We have looked at neural networks earlier in this course. They generally tend to look like this, where you have a layer that expands into another layer that then shrinks back down into a third or output layer. That's exactly what happens in the feed-forward neural network. The connections of these dense layers is presumably where all of this information that models know is stored and modeled and interpreted and interpolated between to enable the models to do the incredible things that they do, to generate code and encode information about the world and speak to you in fluent and coherent language of your choosing. Self-attention, on the other hand, allows the model to attend to previous tokens and incorporate the context in its understanding of the token it's currently looking at. Let's look at this example. Let's say we have a prompt that is, the dog chased the llama because it, when the model is processing the word it needs to bake in some information about what does it refer to here. Is it the dog or is it the llama? It's important for the model to be able to have some sense of what that it refers to. And that's a little bit of what self-attention does. It enables the model to bake in some of that representation of the llama tokens, for example. If the previous context points towards this being the llama, self-attention allows the model to bake in some of that representation of the llama into it. And so while it's processing the token, it has some understanding that this is referring to the llama, quote unquote, understand. This is an NLP task called co-reference resolution. And if these are only the words that are presented to you, it might be difficult to really ascertain, is it the dog or is it the llama? But in this example, let's assume that previous tokens in the prompt indicate that it is the llama. So to understand attention at a high level, let's formulate it like this. So we have other positions in the sequence. So we have previous tokens that we've processed in the past, and then we have the current position that we are processing. We have its vector representation. So this is the embedding if we're in transformer block number 1, but if you're in block number 2 or 3 or 4, this is the output of the previous block. And then towards the end, we want this vector representation that bakes in the relevant information from the other positions here. So here, you're looking at these, let's say, 5 tracks, and we're basically pulling in the right information that is useful to represent this token in this step of the model's processing. So this is a high-level formulation of self-attention. We'll get into more of the specifics in the next lesson. But what self-attention does is 2 things. The first thing is relevance scoring. So it assigns a score to how relevant each of the input tokens are to the token we're currently processing. And then the second step is, after scoring that relevance, is combining the relevant information into the representation. So at a high level, this is what self-attention boils down to. Relevance scoring, and then combining the information from the relevant tokens into the current vector that we're processing and representing. In the next lesson, we'll look at more details of how that's done.
Okay, let that bake in a little bit. Okay, like there was a lot of things covered in the stack of transformer blocks. So let's go through that one by one. So here, let me share my notes. Okay, so the token flow through transformer blocks. Basically, after tokenization, token embeddings are passed through a stack of transformer blocks in sequence. Okay, after tokenization. So that is represented better with this picture. So let me add that to my notes. So here, okay. So after tokenization, so tokenizer generated these tokens. After that, it is passed to the transformer blocks in sequence. Example used, the prompt, the Shashank is broken into the Shashank is broken into 2 tokens, the and Shashank. Each token is replaced with its associated embedding vector. So it is replaced with its associated embedding vector, converting language into numbers for mathematical processing. Tokens flow through transformer blocks one by one. Okay, with each block operating on the outputs of the previous block in parallel across all the token positions. So for this one also, it will generate something, and tokens flow through the transformer blocks one by one, with each block operating on the outputs of the previous block in parallel across all the token positions. The flow is unidirectional from tokenizer through transformer blocks sequentially to the final output. Okay. Output token generation. In decoder LLMs, the generated token is produced from the final token position. Only the token generated after the last token in the input sequence is considered the next predicted token. The final layer presents the vector for the last token to the language modeling head, which outputs the predicted next token. So this is what we concluded in the last section as well. And that's what is reaffirmed here. Transformer block components. Each transformer block consists of the major components, the self-attention layer, and then the feed-forward layer. So these are the 2 layers that are considered. Okay, and let me figure out the representation for that one. So okay. Okay, so this is the self-attention layer and the feed-forward neural network layer. In the feed-forward neural network layer, if a transformer block only had the feed-forward neural network layer without the self-attention, it could still generate completions based on the statistical probability of the next word. Example, the most probable token after Shashank would be redemption based on the training data patterns from the internet and Wikipedia. The feed-forward network serves as a storage of information and statistics about likely next words. Architecture typically consists of layers that expand then shrink back down to an output layer. Okay, the dense layer connections store and model information that enables the model to generate code. encode world knowledge, and produce fluent language. So basically, feed forward neural network layer has the knowledge of the internet, and without attention also it can generate the completions based on the statistical probability. But the self-attention layer, what does it provide? Self-attention layer allows the model to attend to previous tokens and incorporate the context when processing the current token. So basically it helps providing the context, not just the based on the statistical training or based on the data, but it tries to read the current context much more. Example use, the dog chased the llama because it, the model needs to understand it refers to. So like if we don't consider this as a in the context, it is another token. So what comes after the token? Without understanding the context, it's difficult. But here, without understanding the context also, the Shashank next word, it can be redemption. It's easy to predict it. Here the dog chased the llama because it can be a llama or it can be referring to dog as well. So it's important to understand the context. So self-attention enables the model to incorporate the relevant token representations. Example, llama into the current token, it based on the context. This addresses, llama into the current token because it replaces the it in a like it as llama in this current context. This addresses the NLP task of co-reference resolution. Self-attention process, the mechanism processes the vector representations from the previous token positions to create an enhanced representation of the current position. Okay, the mechanism processes the vector representation from the previous token positions to create an enhanced representation for the current position. Okay, got it. Self-attention performs two key functions. Relevance scoring assigns scores to determine how relevant each input tokens is to the currently processed token. Okay, assign scoring to determine how relevant each input token is to the currently processed token, and combines information from relevant tokens into the current vector representation. Okay, got it. Like here, for example, if the dog chased the llama because when we are like processing it will score the relevancy of each tokens that are processed before it to the current processed token, or could be true for because also, like what is the relevance of all these tokens that were processed before this token. Okay, combines the information relevant tokens into the current vector representation. Okay, and it is represented in the numerical format that is there. Let me see if I have any better notes as well. Transformer block, feed forward network. So the feed forward network somewhat looks like this. And the self-attention is needed to get the context. Okay, so this completes it. So we are ready to move on to the next chapter now, which is dedicated on self-attention. Okay, let's start the next chapter, self-attention.
Self-attention is a key component in the transformer block. You've learned that it consists of two steps: relevance scoring and then combining information. You'll now take a closer look at how those are calculated and how that has evolved in recent years to enable more efficient attention. Let's dive in. So by now you know that self-attention breaks down into two high-level steps: relevance scoring and then combining information. Let's look at those in more detail. Self-attention happens within what we call an attention head. So let's assume we only have one of these attention heads right now that we're using to process self-attention. We have the token that we're currently processing, and then we have the other positions in the sequence. So these are the vector representations of the other tokens that precede this token. Self-attention is conducted using three matrices: the query projection matrix, the key projection matrix, and the value projection matrix. For transformers, the queries, keys, and values are important concepts. In this calculation, you'll get a sense of what each of them is used for. These weight matrices are used to calculate query, key, and value matrices. And through some interaction that we'll discuss in the next coming slides, we can go about scoring the relevance and then combining the information. So let's say on the query side here, we have this query that represents the current position. And then this matrix, let's say each row here represents one of the other tokens in the series. And the same thing is done with keys and values. Each row is a vector representing one position in the sequence. The end goal of relevance scoring is something like this. Every token that we have, any score assigned to it, telling us how relevant this token is to the token we're currently representing. In this case, let's say we have the dog that has the highest relevance scoring, and so more of the representations of the tokens and the dog will be baked into the enriched vector here towards the end. But this is the end of relevance scoring, giving us these scores, and they add up to 100. Now, technically, how this is done is by matrix multiplication. We multiply the queries vector associated with the current token by the keys vectors that represent all of the previous tokens. This is a high-level intuition. But if you want to know more about how attention is calculated and implemented, DeepLearning.AI has a short course that is entirely devoted to the calculation and implementation of attention. You can see that on the screen if you want to dive into more details. I highly recommend it. Joshua Starmer is incredible, and I love StackQuest. And then now that we have the relevance scores, we can start with the second step, which is combining information from the relevant tokens. That is done using the values vectors associated with each of these tokens. So each token has a values vector associated with it. We just multiply the score of each token by the vector value. And that gives us these weighted values, where the dog would have the highest value, and then these will be closer to 0 because we're multiplying them by small numbers. And then once we have our weighted values, we just sum them up, and then that is the output of this second information combination step. As we've mentioned, that calculation happens within an attention head. But in self-attention, the same operation happens in parallel in multiple attention heads. Each attention head has its own set of keys, queries, and values weight matrices. And so the attention that they assign to the various vectors is different. So we can think about two components of self-attention. Before splitting into attention heads, there's this step of splitting that information into the attention heads, and then we have a step of combining that information from all of the attention heads back together to form this output of the self-attention layer. It's also important to visualize those keys, queries, and value matrices. So we've said that each one of these attention heads has its own set of projection matrices for keys, queries, and values. And now that you have that visual, we can talk about more recent forms of attention that power the current generation of transformer large language models. To make self-attention more efficient, because this is usually one of the steps that takes the longest and requires the most computational time in transformers. So one idea that was proposed to make attention more efficient is this idea of multi-query attention. And the idea here is that not each attention head has its own keys and values, but no, let's have them all share the same keys matrix and values matrix. So you only have one for the entire layer, one set of these two projection weights matrices. You can think of this as some sort of compression. So we have a smaller number of parameters to calculate all of this, and this helps models be faster when they calculate self-attention. More recently, grouped query attention is an efficient attention mechanism that allows us to use multiple keys and values. Not the same number of attention heads, it's a smaller, lower number, we refer to here as number of groups. And this leads to better results than when we just shared one set of keys and values matrices. This is especially important with larger models that require more of those parameters to represent the data that is required to really do self-attention on very large sets of training data. And so now when you read papers that describe the architecture of the model that they trained, you will find if they use multi-query attention, they will mention how many attention heads that they use, but also how many groups of keys and values that they use. Another important recent idea for improving the efficiency of attention is this idea of sparse attention. And this usually happens not in all layers. So let's say the first layer has self-attention in the way that we just discussed, where token number 7, as we're processing it, is able to attend to all of the tokens that preceded it. In larger and larger models, that becomes a little bit too expensive if you allow that to happen at every layer. So you start to see that maybe interweaved, so layer 2 and layer 4 and layer 6, for example, are not able to attend back to all of the tokens in the history, but maybe to the last 4, or 16, or 32. This is an idea that's called sparse attention. One way to think about it, if we're to set up some visual language, let's say we have the token we're processing it now, so we can't really attend to any previous tokens. But let's say the second token is dog, so dog can attend to both the and dog. And then we have chased, the third token, and that is able to attend to 3 tokens, right? So chased attends to dog and dog. Now this is just to set up the visual language for figures like this that describe what sparse attention looks like. So this is full attention, where every token can attend to every previous token. So you can think of each row as a step in processing. Maybe we generated this token, and then we generated it, where do we attend to? But sparse attention can be like this. This is strided, where at every position you can look back at the last 3 or 4, but then you can also maybe look at the specific positions. So you can look at position number 1 and 4 here, for example. And then another idea of sparse attention is this idea of fixed, where there are these fixed positions in the context sequence that, after you reach token number 4, you're only allowed to look at the tokens from 4 until the current position. This is a figure from this paper, generating long sequences with sparse transformers, that goes a little bit into more detail about how these methods work. More recently, and to allow these models to go through 100,000 or a million token context sizes are ideas like ring attention. And for that, I'd highly recommend you check out this blog post, Ring Attention Explained, that goes through a highly visual and animated explanation of the ring attention and how it works. Congratulations for making it this far. Now that you've seen all of this visual language, when you are reading a paper like this is the most recent, at the time of recording, paper by Meta for the Llama 3.1 models. When you go to the architecture section, you should by now have the visual language to think through all of these parameters that describe the architecture of the model. And so when you look at tables like this, you know what each of these components look like. If we're to take an example and look at this 8B model, you can see that it has 32 layers, which can look like this. So this is a set of how many transformer blocks that it has. It has 4,000 model dimension. That is the dimension length of the vector that flows through the transformer. You see that the feed-forward neural network has a dimension of 14,000. That is how many units are in this part of the feed-forward neural network. You see that it has 32 attention heads, and you know what those are. And you see that it's using grouped query attention with 8 key value heads, and that's the number of groups. You also see that it has a vocabulary of 128,000, and you know how that is represented inside of the tokenizer, and the associated embeddings matrix inside of the model. And you can see that it uses rope for positional embeddings. This is a method called rotary embeddings that we'll talk about in the next lesson.
Okay, so in this section, they covered self-attention. So self-attention is like basically the basic thing to know is like it provides context to the predictions. So without self-attention layer, we can still generate the next word prediction, but mostly based on like what has occurred or what has the best probability only, without getting the context of like what was there before. So let's move on to the nodes and see the self-attention layer. So this session covers self-attention, a key component of the transformer block, explaining its two main steps. One is relevance scoring and combining information. So yeah, that clarifies it. Relevance scoring and combining information. Okay, combining information and recent efficiency improvements. Okay, all those things. Concept of the core concepts of self-attention. Self-attention operates within attention heads and processes token in a sequence. Uses three metrics for calculations: query, key, and value projection matrices. The query represents the current token position, okay, and while keys and values represent the other tokens in the sequence. Okay, so it is somewhat like this. The query projection. So whenever we are processing something, okay, here the query represents the current position in the input, and then the key projection and values projections are like keys are the like other words or the other tokens in the same input or the block, and then value is the relevancy information. Okay, values represent the other tokens in the sequence. Relevance scoring process. Each token receives a relevance score indicating how relevant it is to the current token being processed. Scores are calculated through matrix multiplications, queries vector multiplied by keys vector of previous tokens. Okay, tokens with higher relevance score contributes more to the enriched output vector. For details, attention calculations and implementation, a deep learning AI short course. Okay, so that is recommended. There is a mathematical calculation of the attention. So if we need to know more, we can pursue that course. Information combining step uses value vectors associated with each token to combine the information. Each token score is multiplied by its vector to create the weighted values. Basically, like whenever we are predicting the next token, we need to see the relevancy score as well as the next prediction score. Like both of those combined, we will try to predict the next token. If it is like the probability is more and if it is not relevant, then it doesn't make sense. Or if it is just relevant and if the probability of that next word is less, then also it wouldn't make sense. So we will combine the calculation of both of those to predict the next word. So uses value vectors associated with each token to combine information, and each token score is multiplied by its value vector to create the weighted values. Weighted values are summed to produce the final output of the information combined steps. Multi-head attention. So here, so yeah, multi-head attention. Self-attention operates in parallel across multiple attention heads. Each attention head has its own set of query, key, and value weighted matrices. The process involves splitting information into attention heads, then combining the outputs back together. Somewhat it somewhat looks like this. Current position information and everything. So this is used to improve the efficiency of the calculation of attention. So each set of attention head will have its own queries, keys, and values, and then based on that we will calculate the attention in multiple different heads, and then we will combine all the information from all the heads. And multi-query attention proposed to make self-attention more computationally efficient. Multi-query, okay. Where is it? Multi-query attention. Okay, multi-query attention heads. And then all attention heads share the same keys and values matrices, only one set of for the entire layer. Okay, first thing is this one. Okay, multi-head attention. Okay, and then multi-query is this one. Okay, this is the multi-query attention head. So basically it uses the same keys and values, but the queries will be different for those attentions. And next one is grouped attention mechanism. So in the grouped one, it looks like this. So there are n groups which it is split into, and n attention heads. Okay. So here a more recent efficient attention mechanism uses multiple keys and values, but fewer than the number of attention heads. Groups are smaller than the total number of heads and produces better results than multi-query attention, especially important for larger models with extensive training data. So this will make the training much more efficient. And then sparse attention, this is an easy concept as well. Another efficiency improvement for large models, not implemented in all layers. Typically, alternating layers use sparse attention. Tokens attend only to a subset of the previous token. So basically, if there is a large chunk of input, like we will decide how much farther we need to calculate the relevancy. Like we cannot keep calculating the relevancy for each of the tokens in each individual layer. So that's what this is saying, and there are rules defined for like how far to go and what needs to be calculated. Tokens attend to only a subset of the previous tokens, last 4 or last 16 or 32 tokens, rather than a full history. Different patterns include full attention, every token attends to all the previous tokens. Strided attention, tokens look back at the I think there was a good representation for that one. So here it is. Okay, full attention, and then the strided attention, and then the fixed attention. Full attention is it looks into every token that came previously to this one. Here every fixed number of tokens, like 2 tokens before this one, or it is like every token until this last token or after this last token. So basically if something is split into sentences, multiple sentences in a prompt, so this is looking into every token within that sentence, like that, like, and then it will start new again when the new sentence started. And ring attention enables models to handle very large context sizes, 100k to 1 million tokens. Recommended sources: ring attentions explain, blog post. Okay, reading architecture specifications. Yeah, I think this would help in reading the architectural specifications. Basically, when there is a new paper published, like for example, the example given was something like the the new Llama paper. So the specifications or everything was provided in terms of this one. So here, let's see. Example, the Meta's Llama 3.1 8 billion model architecture. It says layers as 32 for 8 billion, and then number of number of transformer blocks, and 4096 model dimensions. So this is the uh, number of values that each embedding would contain, like a number of values that each embedding would contains, and 14,336 feed forward dimension units in the feed forward network layer. So that neural network that we visualized, number of feed forward layers in that one, and 32 attention heads, number of the parallel attention heads that we just discussed now. 8 key value heads, number of groups for grouped query attention. So the group attention heads, 128,000 vocabulary size. We saw it in the tokenization. So represented in tokenizer and embedding metrics, and ROP, rotary embeddings, methods used for positional embeddings. So yeah, this one we didn't touch, but yeah, that is something. Deep learning AI short course on attention calculation and implementation. Okay, so these are the suggested resource for next one. Let's move on to the next section if nobody has any questions. Let me do some cleanup in my notes before moving on to the next section. Okay, done. So next section is model example. Let's see what it is.
You learned so far about all the different components of the transformer. Now it's time for you to explore the architecture of one model example using the Hugging Face Transformers library. Let's code. To reinforce everything that we've learned so far, let's take a quick look at the code of how Hugging Face Transformers allows us to look at a transformer and its tokenizer and how that process happens that we've looked at. So how the processing and how the flow of information happens from the tokenizer to the stack of transformer decoders to the element, and look at how that works in the code. So let's start with just a couple of logistics. Just want to remove a little bit of these warnings that we're going to see. And then we're going to be loading a language model. So this is the Phi3 mini model. So here we're downloading it with its tokenizer. Since we're using it on a CPU, it's showing us a couple of these warnings, but you can just ignore them. Let's now define a Hugging Face pipeline. So we're saying this is the model that we've downloaded and the associated tokenizer that we've downloaded. So you can see that this is the Phi3 model and this is the Phi3 tokenizer. We pass them both to this pipeline, which is just a code abstraction that makes it easier to generate code within it after we give it and load up the model tokens. And here we're saying that, okay, whenever we give you a prompt, we want you to generate 50 tokens in response to it. The doSample parameter means that we're doing greedy decoding, as we've looked at. So with each token, it would score the probability of the output tokens and it would choose the token with the highest probability. So this is almost exactly like setting the temperatures. Now that we've done that, we can declare our prompt and pass it to the model. Now, this is the prompt that we're giving the model. It's being processed right now. So it's saying, write an email apologizing to Sarah for the tragic gardening mishap, explain how it happened. Now, the model is processing these. Let's skip through to when it's done generating and talk about what it did in the process. And here we see the output. So these are the 50 tokens that the model generated. Email to Sarah and the subject, and then we start to write the body of the message, and then it stopped at the middle of the 50th or last token that it generated. Now you can take that chance to change the prompt to whatever you'd like and see how the model responds. It might take around 2 minutes to generate the output because it's running on CPUs in this example, which is why in industry, a lot of these models actually run on GPUs that are highly optimized. And a lot of these efficiency methods that we've discussed are important to speed up that generation. That's the reason why there's a lot of focus on that efficiency. Now, a lot of people have not used language models beyond just a chat interface or a playground. And so if you're one of these people and this is your first time generating with a language model in code, congratulations. Now you understand these models a little bit better. And if you've seen this in the past, stick around and I'll show you a couple of the cool things that Hugging Face sort of enables you to do in terms of just understanding the hierarchy of the model and how it works together. So a couple of things to point out with Hugging Face is now that we've loaded the model as well, we can just print that, and that will show you the structure, the architecture of the model that we have. And you can see that it's indented. So this shows you the hierarchy. So you have a model. So this is the Phi3 for causal language modeling. This is a decoder model. It is a causal language model, autoregressive, which means that the attention step only focuses on the previous steps. Inside this model, we have two major components. We have the model itself. This is where all of the layers, these are the transformer blocks sit. You have the tokens. So this is the tokens matrix. The model has 32,000 tokens in its vocabulary, and the model dimension is 3072. There are 32 decoder transformer layers, and you can see the exact components of each one of them. So we have self-attention, the projection, the rotary embeddings addition here, the MLP, the multi-layer perceptron is what we call the feed-forward neural network. That is the component here. And you can see that projects it up to the high level dimension, which is 16,000 in this case, and then projects it down to the model dimension of 3,000 again. You have your activation function, and then your layer norm. And then towards the end of the model, you see the language model, and which outputs a vector of dimensions 3072. In the end here, we see the language modeling head, which takes in the final vector of 3072. That's the model dimension. And it outputs a score for each of the tokens that the model has in its vocabulary. Hugging Face also makes it possible to do something like this. So you can browse like this. So now we went into the model itself. We can address all of these layers kind of like this. So we can access the embeddings layer or matrix like this. We can say, okay, let's say we want to do model.layers, and then you want to access the first transformer block, which looks like this. And so this is a way for you to be able to access each of these layers and matrices and see the input size and output for each of these layers, but also access the actual matrices themselves if you want to do. Let's go back to the generation. Let's say we have a simple prompt like this. The capital of France is. Now, we'll process this in a different way. So instead of doing a pipeline, the pipeline sort of abstracted a few things from us. Let's do it in a way where we get to see a little bit of the mechanics of how that information or how the processing is actually done. So we have this code here where we have our prompt, we send it to the tokenizer, and we have it return input IDs. Let's say we wanted to show us the input IDs, and that's the result of the tokenization. So the tokenization said, okay, this one string of text is now broken into these 5 tokens. For number 450, number 7483, and number 310. This is how this information is represented. Now we can send that to the model. And notice here that we are sending this to the model component of the model. So this will not go through the language model. This is just flowing through the stack of transformer. So let's look at how that output looks. It looks something like this. Now you have this tensor of dimensions 1 by 5 by 3072. This is the batch dimension. So we pass the model only one text, and so it processed only one. While in training, you'll have a lot more of these, and so this can be a lot more. 5 is the number of tokens in this sequence, and 3000 is the dimension of the output vectors. Now, to think of this, think about this visual that we've looked at. The vector that we're currently looking at is a matrix that is basically this row and this row together, sort of mushed as, let's say, 2 rows of one matrix. And so 3000 is the number of dimensions for this vector. And then here we have 2, but in here we have 5. So that is the output here, which is the vectors before we hit the language model. We can pass that to the language modeling head independently and then see what that output looks like. Let's look at the shape of this output. And so this is a tensor of 1 by 5 by 32,000. And we see 32,000 now, you know that that is the vocabulary size that we have. And so these are the scores for each of these outputs. But to get the actual output for this string that this prompt that we've sent to the model, this is what we do. So we address the actual vector that we want. So it's the last token in the sequence, and then we pass it to, this will give us the token ID, which is a number. Let's print that here. So the number, the output token, the first output token that the model generates is the token number 3681, and then to decode that back into human language, that is PEPS. And I find that fascinating for 2 reasons. So one is now we have this piece of software that is able to sort of, you can download this piece of software to your computer or your phone, and it's able to tell you information about the world somehow. That can be very complex. But also there's another thing that you can only see here, which is the model really never saw the text. The model only sees these lists of numbers, and it only outputs these lists of numbers. Everything that the model touches is just, this is token number 4 or 4000. It never has seen through the actual letters that we think of. It's fascinating that language models operate in this way, where The model's never really seen human language in ways that we actually see it. It only sees this list of indices of tokens. So this has been a quick look at the code of a Hugging Face language model. In the next lesson, we'll look at other recent improvements to large language models.
I think this was self-explanatory. Like I don't have to spoil it. Like basically, uh, this is a very good example of how we can access and view the internals of the models and the details, and also like it was fascinating to see like how the model has only numbers or the token IDs that is passed along across the different parts of the neural network and the model architecture, and then it comes out with the exact word finally as an output, which is accurate. Like it has that condensed information of or condensed knowledge of the entire world compressed within it, and then based on the calculation it is able to fetch that one and provide it as an output. So that is fascinating to see. I think this would be a good conclusion for this live stream, I guess. Like we learned a lot about the internals of the transformers and how the LLMs work. So this is a good basics. Next, I think we are ready to move on to either go get back to the basics of neural networks, or we can move ahead to the application part side of it, like dive deep into agentic AI or model context protocol or something like that. Or we can I'll have a thread in both. Like if we go to one of the threads, it might get overwhelming. So we will keep learning the basics as well, and at the same time application level details or application level, whatever the information we needed to develop that, I think we got that covered in the basics already. So we are good to go. So this has been a good session, and thanks to DeepLearning.AI for making it available for all the students. Thank you. We'll see you guys very soon. Keep learning. Thank you.